Imagine that the universe exists in a state of false stability, like a ball resting precariously on the side of a hill rather than in the valley below, and that this precarious arrangement could collapse at any moment without warning or mercy. This is the essence of vacuum decay, a theoretical physics concept that suggests the very fabric of reality itself, the quantum vacuum that permeates all of space and undergirds every particle and force we know, might not actually be in its lowest and most stable energy state. According to this hypothesis, our universe could be trapped in what physicists call a false vacuum, a temporary state of relative stability that is, in fact, just one notch above true stability on an energy landscape that stretches across countless possibilities. Deep within the mathematics of quantum field theory, particularly in the context of particle physics and the Standard Model, there exists the possibility that the Higgs field, the fundamental field responsible for giving particles mass, might not be stable forever. If a random quantum fluctuation in some remote corner of the cosmos were to bump this field into a lower energy state, a bubble of true vacuum would begin to expand at the speed of light, traveling outward in all directions from that singular point, and everything within it would be fundamentally and irreversibly transformed. The physics inside this expanding sphere would be different from the physics we know. The constants of nature would change, particles would behave differently, atoms could not form as they do now, and all matter and structures dependent on current physics would simply cease to exist in any recognizable form. The strangest and most unsettling aspect of vacuum decay is that we would have no warning whatsoever, no time to prepare, no philosophical framework adequate to the moment, because the collapse would travel at light speed itself, meaning the wavefront of destruction would arrive at Earth before any information about its occurrence elsewhere could reach us. We would be erased from existence instantaneously, in absolute darkness, without comprehension or transition. The mechanism behind why physicists take this seriously despite its seemingly fantastical nature lies in the straightforward mathematics of quantum field theory, which makes no guarantee that any field is in its true ground state, and in fact suggests, given enough time and enough quantum fluctuations across an infinite or near-infinite universe, that such an event becomes not just possible, but perhaps statistically inevitable. Yet despite this theoretical threat existing within our best current understanding of physics, despite papers published in peer-reviewed journals discussing vacuum decay probabilities, we have normalized this existential danger so completely that it occupies almost no space in our daily consciousness, no room in our cultural anxieties, no presence in our collective imagination in the way that more immediately threatening phenomena do. Imagine a universe where the very fabric holding reality together begins to unravel, not in a single catastrophic moment, but across an incomprehensibly vast span of time, slowly tearing itself apart from the largest structures down to the smallest particles, a process so gradual and inevitable that it represents perhaps the most genuinely unsettling endpoint our cosmos could possibly face. The Big Rip theory emerges from our observations of dark energy, that mysterious force that appears to be accelerating the expansion of the universe rather than slowing it down as gravity would predict. And if dark energy's strength increases over time rather than remaining constant, then the expansion rate would accelerate exponentially, until eventually the repulsive force becomes so powerful that no bound structure could possibly hold together. First, the most distant galaxy clusters would separate from our observable universe as the space between them stretches faster than light itself could travel to bridge the gap. Then on timescales of trillions of years, the expansion would continue until even our own Milky Way would be torn apart, stars ripped away from one another and scattered across an infinitely expanding void. Then planets would be stripped from their orbits, torn from their parent stars, and flung into the cold darkness of space. As the acceleration continued, the immense gravitational binding forces holding planets together would eventually be overwhelmed by the relentless expansion of space itself, causing worlds to disintegrate and crumble, and then on even shorter timescales, atoms themselves would be stretched and torn apart, their electrons separated from nuclei, until matter itself ceased to exist in any recognizable form. What makes this theory psychologically compelling despite its purely speculative nature is that it transforms the universe's expansion, which we perceive as an abstract mathematical phenomenon, into something visceral and tangible, a genuine apocalyptic violence occurring across cosmic distances, and the concept resonates with a deep human anxiety about dissolution and the inability to hold onto anything as everything progressively deteriorates. The Big Rip also represents the inverse of the Big Bang in a way that satisfies a certain symmetry in how we think about universal narratives, moving from a state of incomprehensible density to one of incomprehensible emptiness, from maximum concentration to maximum dispersion, and this mirror image quality gives the theory an almost narrative satisfaction. Yet despite being merely one possibility among many theoretical endpoints for the universe, and despite requiring assumptions about dark energy that remain unproven and potentially incorrect, the Big Rip persists in scientific discourse and popular imagination as though it were somehow uniquely probable or especially likely, perhaps because its sheer scale and absolute nature makes it memorable in ways that more moderate cosmic deaths simply are not. In the deep mathematics of thermodynamics and quantum mechanics lies a peculiar and unsettling thought experiment that emerges from the work of 19th-century physicist Ludwig Boltzmann, one that suggests that the universe might be populated not by ordinary beings like ourselves, but by disembodied conscious minds that spontaneously materialize from the quantum foam for mere moments before dissolving back into entropy. Imagine a universe that has reached its final state of maximum entropy, a place of absolute darkness and cold where all energy has been evenly distributed and all structure has decayed beyond recognition. Yet in this seemingly dead realm, quantum fluctuations continue to occur infinitesimally and randomly throughout eternity. And occasionally, through sheer statistical improbability, these fluctuations coalesce into the precise arrangement of matter and energy required to produce a functioning brain. Complete with memories, thoughts, and the sensation of consciousness, only to immediately dissipate once more into the universal heat death. The mechanism underlying this troubling scenario rests upon a fundamental principle of statistical mechanics. Given an infinite amount of time and infinite possible states, even the most improbable configurations will eventually occur, and a disembodied brain capable of thought and sensation requires far fewer particles and far less energy to exist than an entire organism or civilization, making it statistically more likely to spontaneously form than any other complex structure. What makes Boltzmann Brains truly philosophically unsettling is that this theoretical prediction, derived rigorously from well-accepted physics, suggests that in the incomprehensibly distant future, most conscious experiences in the universe will not belong to beings who have lived full lives or built civilizations, but to random, isolated brains that flicker into existence experiencing confusion and despair before winking out forever. And yet, despite the profound implications of this scenario for our understanding of consciousness, meaning, and the nature of existence itself, we have largely normalized and compartmentalized this theory as a curious mathematical artifact rather than confronting the strange and melancholic picture it paints about the ultimate destiny of awareness in the cosmos. Perhaps most troublingly, this logic suggests that if we ourselves are conscious beings perceiving what appears to be an ordered universe with physical laws and history, we are statistically far more likely to be Boltzmann brains experiencing an illusory sense of continuity and causality than to be genuine products of the universe's early conditions. A realization that transforms the thought experiment from a distant cosmic concern into an immediate epistemological crisis about the reliability of our own perceptions and memories. Consider for a moment the peculiar notion that our universe, in all its vast complexity and apparent permanence, might be nothing more than an elaborate computational simulation running on some incomprehensibly advanced hardware, and that one day, the architects or operators of this simulation might simply decide to shut it all down, to power off the entire cosmos like closing an application on a computer. This theory posits that reality, as we know it, could terminate not with a bang or a whimper born from physical laws, but rather due to a conscious decision made by beings existing outside our dimensional framework, entities so far removed from our understanding that they would be indistinguishable from gods. The psychological mechanism underlying this fear operates on a fundamental level of human anxiety about control and powerlessness, tapping into our deep unease about being subject to forces entirely beyond our comprehension or influence, about the possibility that our existence is contingent upon the whims of external powers rather than rooted in any inherent or stable reality. We find ourselves drawn to this concept because it crystallizes a modern existential dread, translating ancient religious fears about divine judgment into contemporary technological language, making our deepest uncertainties about existence feel somehow more rational by dressing them in the vocabulary of computer science and digital architecture. The persistence of simulation shutdown theory in contemporary discourse reflects how readily we accept the premise that our reality might be fundamentally less real or less consequential than we intuitively assume, and how the advancement of technology has paradoxically made it easier to imagine that nothing we experience is genuine, that the bedrock of our existence might be nothing more than a vast mathematical operation that could be terminated at any moment. Yet we continue building civilizations, raising families, and pursuing projects of meaning despite harboring this possibility in our collective consciousness, demonstrating humanity's remarkable capacity to coexist with existential uncertainty while still asserting that our choices and lives matter, whether or not we inhabit a substrate of silicon and light rather than atoms and energy. Perhaps this is why the simulation shutdown scenario, despite its theoretical plausibility, fails to paralyze us. We intuitively understand that whether our reality is substrate independent or not, the experience of living it remains irreducibly real, and the meaning we generate through our actions persists regardless of what lies beneath the surface of existence. Imagine the universe as a vast collection of delicate dominoes stretching across incomprehensible distances, each one representing the stability of matter itself as we understand it, and then consider the possibility that somewhere in the cosmos, perhaps already occurring right now in some distant corner of space, a single domino falls that can never be set upright again. This is the essence of the strange matter cascade theory, a concept that emerges from our deepest understanding of particle physics and the fundamental nature of matter itself. Strange matter is a hypothetical state of matter that could theoretically exist at the cores of neutron stars or be created in high-energy collisions, composed of quarks in a configuration that is somehow more stable than ordinary matter. The cascade occurs when a chunk of strange matter comes into contact with ordinary matter, causing a chain reaction where the strange matter converts normal atomic nuclei into strange matter at the speed of light, propagating outward like an unstoppable wave of transformation. What makes this theory particularly unsettling is its logical foundation in established physics, emerging not from pure speculation, but from careful mathematical models of quark behavior under extreme pressure and density. The psychological mechanism behind why this theory persists despite its terrifying implications is rooted in our peculiar human relationship with distant possibilities, a phenomenon where we can acknowledge the mathematical possibility of total annihilation without truly integrating that knowledge into our emotional understanding of reality. We have normalized the existence of such doomsday scenarios in our scientific literature and popular discourse, mentioning them in the same breath as black holes and supernovae, as though simply cataloging existential threats somehow diminishes their significance. The probability of such an event is extraordinarily small, which our minds grasp intellectually, while our consciousness quietly files the concept away alongside other low-probability catastrophes, creating a strange equilibrium where we remain simultaneously aware and unbothered by the theoretical possibility that reality itself could be fundamentally transformed by one chance cosmic encounter. Yet this cognitive dissociation serves a purpose, allowing us to contemplate the deepest uncertainties of existence without descending into paralysis, to hold both the fragility and resilience of reality in our minds simultaneously, much like how we live our daily lives knowing that the sun will eventually consume the earth, yet we still make plans for tomorrow. And perhaps this is the most rational response available to us, to acknowledge that some dominoes may fall beyond our control or perception, and to recognize that our inability to prevent every theoretical catastrophe is not a failure of science or foresight, but simply a condition of existing in a universe governed by probability rather than certainty. Imagine the universe not ending in a cold, lonely dissolution into darkness, but instead collapsing backward upon itself like a reverse of its own birth, a cosmic implosion where all matter and energy compresses down into an infinitely dense singularity, reversing the expansion that has defined existence for nearly 14 billion years. The Big Crunch represents one of the oldest and most geometrically satisfying theories about the universe's ultimate fate, emerging from the mathematics of general relativity and the observation that gravity, that fundamental force which pulled matter together into galaxies and stars and planets, might ultimately prove stronger than the expansion that drives everything apart. In this scenario, the expansion of the universe would slow, stop, and then reverse, with galaxies hurtling back toward each other at accelerating speeds, crushing and colliding in an increasingly violent cosmic compression that would heat the universe to temperatures that dwarf anything we can currently imagine. Stars would merge with stars, galaxies with galaxies, all structure dissolving into a plasma of fundamental particles before finally reaching that final singular point of absolute density and infinite temperature, a mirror image of the Big Bang that created everything in the first place. The psychological appeal of this theory lies in its narrative symmetry, in how it offers a kind of cosmic closure and balance to existence, suggesting that what begins must end, and that endings can echo their beginnings in profound and elegant ways. There is something deeply satisfying about the idea of a universe that completes itself, that forms a perfect cycle from creation through expansion to contraction and final collapse, a system that appears to respect a kind of universal law of conservation where the beginning and end are mirror images. This symmetry resonates with human storytelling instincts, with our preference for narratives that have clear conclusions and poetic justice, with mythological patterns where destruction precedes renewal and endings generate new beginnings. The Big Crunch appeals to our desire for cosmic drama, for a universe that doesn't merely fade but rather goes out in a spectacular and cataclysmic finale, and perhaps most fundamentally, it offers the comfort of determinism, the idea that the universe's end is already written into its beginning, that fate and structure govern even the largest scales of existence. Yet the Big Crunch has gradually receded from scientific prominence as observations have consistently demonstrated that the universe's expansion is accelerating rather than slowing, driven by an enigmatic dark energy that appears to permeate all of space and push matter apart with increasing force, suggesting instead a cold, infinite expansion toward maximum entropy and absolute zero. Imagine that the universe as we know it exists in a state that is not actually the lowest possible energy state, that everything around us from the smallest particle to the largest galaxy is perched precariously on a cosmic hillside, waiting for the slightest nudge to tumble down into something far more stable and entirely destructive. This is the concept at the heart of the false vacuum theory, a notion that emerged from quantum field theory and has haunted theoretical physicists for decades with its unsettling implications about the fundamental nature of reality itself. The idea suggests that the vacuum of space, that seemingly empty nothingness that constitutes most of the universe, could spontaneously collapse into a lower energy state, and when it does, an expanding bubble of true vacuum would race outward at the speed of light, obliterating everything in its path and fundamentally rewriting the laws of physics as it goes. Within this expanding sphere of destruction, the very constants that govern atomic structure and chemical bonding would shift so dramatically that atoms themselves would cease to exist in any recognizable form. Atoms would simply fly apart as if the forces holding them together had been switched off, which in a sense they would have been. The psychological grip of this theory lies partly in its elegant simplicity and partly in what it reveals about the uncertainty built into our understanding of the cosmos. For it suggests that our universe might be a temporary accident, a bubble of relative stability floating in an ocean of potentially hostile physics that could erase everything given the slightest opportunity. We have normalized this anxiety by treating it as a purely academic concern, something that physicists discuss in peer-reviewed journals, while the rest of humanity goes about their daily lives unaware that their existence could end not with a bang or even a whimper, but simply with the laws of nature quietly switching themselves off. Yet the theory persists because it emerges naturally from our best mathematical descriptions of how particles and fields actually behave, suggesting that the danger, however remote, is genuinely written into the fabric of reality itself. The closest we might come to witnessing such an event would be in the aftermath of the Big Bang itself, where the universe is thought to have undergone just such a transition, dropping from one energy state to a lower one in the first fraction of a second of existence, a process that may have driven the cosmic inflation that shaped everything we observe today. In this sense, the false vacuum is not merely a threat hanging over our future, but a ghost haunting our past, a reminder that the universe we inhabit may owe its very existence to the same catastrophic mechanism we fear could one day destroy it. Imagine a point in space where all the laws of physics as we understand them cease to function, where time itself becomes meaningless, and where the very fabric of reality tears open to reveal something that should remain forever hidden behind the protective veil of an event horizon. This is the concept of the naked singularity, a theoretical endpoint of cosmic collapse where a dying star or black hole loses its outer boundary and exposes its infinitely dense core directly to the observable universe. In the traditional understanding of black hole physics, the singularity, that point of infinite density where matter is crushed beyond all comprehension, remains forever cloaked behind the event horizon, a boundary from which not even light can escape, protecting the rest of the cosmos from the direct effects of this mathematical catastrophe. But in certain scenarios involving rapidly rotating objects or unusual matter configurations, physicists have theorized that this protective boundary might fail to form, leaving the singularity exposed and naked to the rest of space. The mechanism behind why this matters lies in the principle of cosmic censorship, a conjecture proposed by physicist Roger Penrose suggesting that nature itself prevents naked singularities from existing through some unknown but powerful regulatory mechanism, as though the universe maintains its own internal consistency through cosmic laws we have yet to fully comprehend. If naked singularities could somehow proliferate throughout the cosmos, spreading from one gravitational collapse to another, the implications would be catastrophic beyond measure, as the gravitational effects of exposed infinities could warp spacetime in unpredictable ways, create cascading failures in the structure of reality itself, and potentially unravel the orderly mathematical principles upon which the entire universe depends. What makes this theory particularly unsettling is that we continue to accept its possibility despite having absolutely no observational evidence that naked singularities actually exist anywhere in our universe, and despite the strong intuition among physicists that Penrose's conjecture is likely correct, we maintain research programs investigating their properties and their potential consequences, as though preparing for a threat that nature itself appears to have already prevented. Yet this paradox of studying something that likely cannot exist reveals something profound about the scientific mind. Our compulsion to understand the boundaries of reality, even those boundaries that may be fundamentally unknowable, suggests that the act of contemplating cosmic catastrophe, however theoretically improbable, serves a deeper purpose in forcing us to question what we truly understand about the universe's foundational rules. Imagine the universe not as something that ends in heat death or a cataclysmic collapse, but rather as an eternal cosmic pendulum, swinging back and forth through cycles of expansion and contraction, each one preceded and followed by another in an infinite regression of births and deaths that stretches both backward and forward through time without beginning or end. This is the Big Bounce theory, a cyclical model of cosmology that suggests our universe is merely one chapter in an endless book of universal existence, where the Big Bang was not the beginning of everything, but rather the rebound from a previous universe's contraction, and where our own ultimate fate involves not an ending, but a transformation into the next cycle's beginning. In this framework, the universe expands for billions of years, galaxies spreading apart and stars burning out, until eventually the expansion slows and reverses, gravity overwhelming the outward momentum and pulling all matter back together in an event mirror to the Big Bang, a moment of incomprehensible density and heat that bounces back into another expansion, another universe fundamentally similar yet ultimately distinct from the one before. The psychological appeal of this theory rests upon something deeply human: our resistance to true endings and our comfort with cyclical narratives, the notion that destruction contains within it the seeds of renewal, that death is not cessation but transformation, and that infinity itself can be found not just in linear time, but in the pattern of eternal return. We have built mythologies around this concept for millennia, from Hindu cosmology's eternal cycles of creation and destruction to the phoenix rising from ashes, and the Big Bounce offers modern physics an opportunity to validate this ancient intuition, to suggest that the universe itself operates according to rhythms we have always sensed but never proven. Yet the theory persists in scientific discussions despite considerable problems. Quantum mechanics suggests information would be lost in the bounce. The universe appears to be expanding faster rather than decelerating toward contraction, and the very concept of time becomes philosophically murky when applied to events that precede our universe's supposed origin. Nevertheless, the Big Bounce endures as a serious subject of theoretical work and popular imagination alike, perhaps because it offers something the heat-death scenario does not: hope, purpose, and the comforting suggestion that our universe's ending is not truly an end at all. In this sense, the Big Bounce represents not merely a cosmological model, but a philosophical statement about meaning itself. The assertion that a universe need not be eternal in the linear sense to possess purpose, that cycles of destruction and renewal might grant existence a dignity that an infinite, unchanging stasis could never provide. Imagine standing in a vast, empty universe where all the stars have long since burned out, where galaxies have scattered beyond the reach of one another, and where the temperature of space itself has cooled to nearly absolute zero, hovering just fractions of a degree above the theoretical minimum possible temperature that can exist anywhere in the cosmos. This is the concept known as heat death, one of the most profoundly unsettling theories about how the universe might ultimately end, and it emerges from our most rigorous understanding of thermodynamics and the fundamental laws that govern energy itself. Heat death proposes that over an incomprehensibly vast span of time, entropy throughout the universe will continue to increase until it reaches a maximum state, at which point all matter and energy will be evenly distributed across space, with no temperature gradients, no motion, no possibility for work to be performed, and therefore no possibility for anything resembling life or change or meaning to continue existing in any form whatsoever. The psychological mechanism that allows this theory to persist in our consciousness, despite its almost unbearable implications, rests upon our natural human tendency to intellectualize catastrophe, to transform visceral dread into abstract scientific language, and to compartmentalize existential threats by studying them from the safe distance of theoretical physics. We discuss heat death in seminars and documentaries with the same clinical detachment we might apply to discussing weather patterns or geological formations, never quite allowing ourselves to fully internalize what it truly means to contemplate the absolute cessation of all potential, all possibility, all distinction and differentiation forever. What makes heat death particularly remarkable is that unlike many apocalyptic scenarios that depend upon specific conditions or catastrophic events, heat death appears to be not merely possible, but rather inevitable according to our best understanding of thermodynamic principles, a conclusion we have somehow managed to normalize and accept as simply another fact about reality. Tucked away in the corner of our collective scientific consciousness, like an uncomfortable truth we have agreed to acknowledge without allowing it to disturb our daily functioning. Yet there is a strange comfort buried within this bleakness. Heat death is so distant, trillions upon trillions of years away, that it exists beyond the horizon of human concern, a theoretical endpoint so remote that it functions less as a genuine threat and more as a philosophical mirror in which we can safely examine our anxieties about meaning, impermanence, and the ultimate futility of cosmic existence without being compelled to alter how we live our lives in any meaningful way. Imagine that somewhere beyond the edge of observable reality, another universe exists in perfect parallel to our own, operating according to its own physical laws and containing its own galaxies, stars, and worlds. And then imagine that these two universes, moving through the vast fabric of higher dimensional space like two ships on an infinite ocean, gradually begin to drift toward one another across the eons. Their trajectories converging inexorably until the moment comes when the membrane separating them grows thin enough to touch. The collision would not announce itself with sound or light as we understand them, but rather as a fundamental rupture in the fabric of spacetime itself, a cascade of exotic particles flooding through the barrier between realities, rewriting the laws of physics at the point of contact and spreading outward like a wave of cosmic restructuring that would eventually engulf everything we know. The mechanism behind this theory rests on the mathematical framework of string theory and the concept of the multiverse landscape, which proposes that countless universes might exist in higher dimensional space, each separated by thin membranes called branes that could theoretically vibrate, interact, and even collide if their paths through higher dimensions intersect. This idea emerges from the legitimate physics of how extra dimensions might function, how gravity could leak between parallel realities, and how the fundamental constants of nature might vary from universe to universe depending on how those branes are positioned and what occurs within them. Yet despite having no observational evidence whatsoever, despite existing in the realm of pure mathematical speculation, this theory persists in scientific literature and popular imagination because it represents an intellectually coherent extrapolation of existing mathematics, because it addresses genuine puzzles in physics like why our universe's constants appear so finely tuned. And because we have somehow normalized the idea that infinite parallel universes might exist as a reasonable working hypothesis rather than pure metaphysics. And perhaps that normalization itself reveals something about the modern scientific mind, our willingness to entertain scenarios of cosmic catastrophe that we cannot measure or test, as though the mathematical elegance of a theory grants it provisional reality, as though a universe-ending collision between realities deserves serious consideration simply because the equations do not forbid it. Yet if such a collision were to occur at the edge of our observable universe right now, expanding outward at the speed of light, we would have no way of knowing until the wave of restructured physics reached us. No warning, no escape, only the gradual realization as our instruments began to malfunction and our understanding of reality itself started to unravel that we had been living in borrowed time all along. Imagine the universe as we understand it existing not in 3 dimensions of space plus time, but rather as a thin membrane floating through a higher dimensional space that we cannot perceive or directly access. And imagine further that this membrane, which physicists call a brain, is not alone in this vast extra-dimensional void, but rather shares this space with countless other brains, each one potentially harboring its own universe with its own laws of physics and its own forms of matter and energy. The Brane Collision theory suggests that our universe's ultimate fate might come not from within itself, through entropy or through the expansion of dark energy, but rather from an external catastrophe of truly cosmic proportions, where another brain traveling through higher dimensional space makes contact with our own, resulting in a collision so violent and so complete that it would annihilate the very fabric of reality as we know it. This idea emerges from string theory and related frameworks in theoretical physics, which propose that the fundamental constituents of reality are not particles, but rather vibrating strings, and that these strings exist within a space that contains many more dimensions than the 4 we directly experience. According to this framework, brains are the objects upon which strings can vibrate and end, and the dimensions we perceive may simply be the ones to which our particular brain is confined. The psychological appeal of the Brane Collision theory lies partly in its radical otherness, the way it presents a threat that comes from literally outside our perceivable universe, from a direction that our senses cannot detect and our instruments cannot easily measure, which taps into that deep human anxiety about hidden dangers and invisible forces. It also possesses a certain mathematical elegance that makes it compelling to theoretical physicists who work with these higher dimensional models daily, lending it an air of scientific legitimacy despite being entirely speculative and having no observational evidence to support it whatsoever. What makes this theory particularly interesting is how it reveals the boundaries of human cognition, for we are asked to imagine dimensions and spaces that exist beyond the reach of our minds, beyond our ability to visualize or conceptualize in any meaningful way. Yet physicists continue to work with these models because they possess internal mathematical consistency. The Brane Collision scenario has persisted in the scientific imagination for decades now, despite remaining utterly untestable and unfalsifiable through any conceivable experiment or observation we might perform. Yet it continues to be explored in serious physics literature, discussed at conferences, and used as a framework for thinking about cosmology, suggesting that we have become comfortable holding ideas that transcend the boundary between science and pure speculation. Imagine standing at the edge of infinity, watching as the universe, in all its unfathomable complexity, slowly winds down toward heat death and absolute entropy, only to discover that given enough time, an incomprehensibly vast duration stretching far beyond the lifespan of stars, galaxies, and black holes themselves, the universe might spontaneously reassemble itself into its exact current configuration, recreating this precise moment in time with perfect fidelity. Down to the last atom and every quantum fluctuation within it, and then it would happen again and again, cycling through an infinite series of identical universes stretched across eternities, a concept known as Poincaré Recurrence that emerges directly from the mathematics of closed systems and thermodynamics. The mechanism behind this theory rests on a deceptively elegant principle. If a system contains only a finite number of possible states, and time itself is infinite, then eventually that system must return to a state it has occupied before, a logical inevitability as ironclad as saying that if you shuffle a deck of cards infinitely many times, you will eventually reconstruct its original order, and by extension. Our finite universe with its finite number of particles and finite number of possible configurations must eventually cycle back to its present state, meaning everything you have ever experienced, every conversation, every loss, every moment of joy would recur in precisely identical form an infinite number of times. What makes this concept particularly unsettling and paradoxically beautiful is that it undermines our intuitive sense that time moves toward something irreversible and final. That entropy represents a one-way arrow pointing inexorably toward disorder and ending, yet the mathematics suggests something far stranger. That at cosmic scales beyond human comprehension, even entropy itself might be cyclical, that the universe does not truly end, but rather loops back upon itself in an endless, deterministic rhythm that has neither beginning nor conclusion in any meaningful sense. We continue contemplating the implications of this theory despite its philosophical vertigo, perhaps because it reveals something profound about the structure of reality itself, suggesting that what we perceive as progress and change might be, from a sufficiently distant perspective, merely different manifestations of an eternal, unchanging cosmic cycle that has always existed and always will exist, a notion that transforms our entire understanding of time, causality, and the meaning of existence itself. Yet perhaps this is not cause for despair, but rather a strange form of cosmic comfort. If the universe is truly cyclical, then nothing is ever truly lost, no moment ever truly dies, and consciousness itself, wherever it emerges in this vast recurrence, participates in an immortality of sorts, eternally reliving and recreating itself across the infinite expanse of time. Imagine, for a moment, that our universe is not the beginning of all things, but rather the interior of a black hole, born from the collapse of matter in some parent universe that exists beyond our capacity to perceive. This idea, known as black hole cosmogenesis, suggests that each black hole that forms in any universe contains within it the seeds of an entirely new universe, complete with its own laws of physics, its own stars and galaxies, and potentially its own conscious observers wondering about their own origins. The theory proposes that what we experience as the Big Bang was not an absolute cosmic beginning, but rather the moment we crossed the event horizon of a black hole belonging to some larger, older, perhaps infinite chain of nested universes, each one containing black holes that birth new universes in turn. This recursive structure creates a kind of cosmic genealogy where universes reproduce through gravitational collapse, where death in one realm becomes genesis in another, and where the boundary between creation and destruction dissolves entirely. The mechanism behind this theory rests on a seemingly elegant mathematical correspondence between the thermodynamic properties of black holes and the expansion dynamics of the early universe, suggesting that the mathematics describing a black hole's interior might be fundamentally identical to the mathematics describing our cosmos. Physicists have noted that the entropy of a black hole and the entropy of the early universe follow similar scaling laws, and that certain solutions to Einstein's field equations permit a natural interpretation where what appears as a singular point in one universe appears as an entire cosmos in another, connected through the deep mathematical structure of spacetime itself. Yet despite its mathematical intrigue, the theory persists in a state of unprovable speculation, untested and perhaps untestable, existing more as a philosophical meditation than as a scientific framework with empirical consequences. We have normalized this idea within certain circles of theoretical physics and cosmology, treating it with the same weight as established models, perhaps because it offers a strange comfort, a way of transforming the terrifying finality of black holes into something generative and continuous, converting cosmic death into cosmic birth, suggesting that even as our universe ages toward its own eventual darkness, it might be quietly nurturing new worlds within its collapsing stars. And if this is true, then somewhere in the distant future, when our own sun collapses and our galaxy spirals toward oblivion, the black holes we leave behind will be seeding universes whose inhabitants might one day wonder, as we do now, whether they too are living inside something vast and ancient, whether their existence is primary or derivative, whether the question of origin is even coherent when causality itself might be circular across the scales of nested realities. Imagine that our universe, vast and ancient as it appears to us, is merely a juvenile offspring spawned from the quantum fluctuations of a parent cosmos that existed before our Big Bang, and that somewhere in the distant future, our own universe will give birth to countless baby universes that bud off like cells dividing, each one with its own set of physical laws, its own arrow of time, and its own inevitable fate. This is the concept of cosmic reproduction, a theory that extends the logic of quantum mechanics and eternal inflation to suggest that universe creation might be an ongoing reproductive process, where pocket universes spontaneously nucleate from the quantum foam of parent universes, each inheriting some characteristics while diverging wildly in others. The mechanism emerges from combining several existing theories in physics, particularly the inflationary model of cosmic expansion, which proposes that space itself has the capacity to inflate exponentially, and the many worlds interpretation of quantum mechanics, which suggests that probability branches create alternative realities at every quantum event. From this perspective, a universe does not simply end. Instead, it becomes the garden soil from which new universes grow, propagating endlessly through an infinite multiverse ecosystem where creation is not a singular event, but rather a continuous process of biological-like reproduction occurring across the fabric of reality itself. What makes this theory persist in scientific and philosophical discourse, despite its almost complete untestability, is that it provides a seductive answer to some of humanity's deepest questions about origins and purpose, suggesting that universes are not merely random accidents, but participants in a cosmic cycle of generation and decay, and further implying that perhaps we ourselves might eventually generate universes, transforming humanity from insignificant observers into participants in the grand process of cosmic creation, an idea so profound and psychologically compelling that we have incorporated it into our contemporary mythology surrounding the ultimate fate of all things. Yet this vision of reproductive cosmology also forces us to confront a humbling paradox. If universes can indeed spawn universes, then the chain of causality stretches backward infinitely with no discernible origin, suggesting that asking what created the first universe may be as meaningless as asking what lies north of the North Pole, and that perhaps the universe's existence requires no external creator because creation itself is simply what universes fundamentally do. Imagine a universe that does not end in a single catastrophic moment, but instead transitions seamlessly into an infinite succession of new universes, each one emerging from the infinite future of the one before it. A concept proposed by theoretical physicist Roger Penrose in the early 2010s that suggests our cosmos operates not as a linear timeline with a definite beginning and ending, but rather as a cyclical cascade where the far distant future of one eon becomes the distant past of another, creating an eternal pattern of cosmic rebirth that continues without interruption or boundary. In this framework, the universe expands infinitely and cools to such an extreme degree that the distinction between space and time becomes meaningless. And at this point of infinite expansion and infinite age, the mathematics of the universe begin to look identical to the mathematics of an infinitely hot and dense beginning, which is to say that the infinite future of one universe becomes indistinguishable from the infinite past of the next, allowing for a kind of cosmic recycling where all the information and structure of one universe feeds directly into the creation of its successor, a process that repeats endlessly without requiring an external cause or initial condition. The psychological appeal of conformal cyclic cosmology lies in its elegant rejection of ultimate finality, offering instead a vision of perpetual renewal that resonates deeply with cyclical mythologies found across human cultures and spiritual traditions, where death and endings are reframed as transitions rather than terminations, and the anxiety produced by contemplating true nothingness is replaced by the comfort of knowing that something always emerges from what came before. Yet despite its mathematical rigor and the serious consideration it receives within theoretical physics circles, this theory has gained relatively little traction in mainstream cosmological discourse, partly because it remains difficult to test observationally and partly because the physics community has largely coalesced around the lambda cold dark matter model and inflationary theories, which have achieved consensus status through their explanatory power and compatibility with existing data. And so conformal cyclic cosmology persists as a fascinating intellectual possibility that few actively champion, a reminder that in science, as in other domains, even sophisticated and elegant theories can find themselves relegated to the margins simply through the accumulation of practical and institutional preferences for alternatives. Imagine a universe where time does not gradually slow, freeze, or reverse, but rather simply ceases to exist in a manner so complete and instantaneous that the very concept of causality becomes meaningless, and what we perceive as the progression of moments simply stops occurring without warning or fanfare, leaving behind a kind of eternal present moment frozen in whatever state the universe happened to occupy at the precise instant of cessation. The notion that time is not a fundamental feature of reality, but rather an emergent property that could theoretically be switched off like a light, suggests that all the mechanisms we associate with entropy decay, and the arrow of time would vanish in an instant, leaving particles suspended in their final configurations with no capacity to move, interact, or change in any way whatsoever. This theory operates on the psychological premise that we treat time as an obvious and permanent fixture of existence, when in fact it may be far more fragile and contingent than our intuition suggests, and that the universe might function perfectly well in a state of absolute temporal stasis, where nothing happens because the very substrate upon which happening depends has simply evaporated. We have normalized the assumption that time will continue indefinitely into the future, building our entire conceptual framework around the belief that tomorrow will arrive with the same regularity as today has. Yet nowhere in the fundamental laws of physics is this continuation actually guaranteed or enforced by any mechanism that would prevent time from simply ceasing to flow. The reason this peculiar theory persists despite its logical implausibility is that it touches upon a genuine philosophical uncertainty about the nature of time itself. For we do not fully understand whether time is truly fundamental or merely an illusion generated by our consciousness and the structure of causality. And if it is merely emergent, then its cessation becomes theoretically possible, even if practically inexplicable. The concept invokes a kind of existential vertigo because it suggests that reality itself operates without any safety mechanism that ensures continuity, that the universe has no obligation to keep time running, and that at any moment the entire machinery of existence could simply halt without cause, warning, or explanation, leaving us frozen in an eternal snapshot of a moment we would never know had become permanent. Yet perhaps the deepest discomfort this scenario provokes is not the fear of non-existence, but rather the recognition that we would have no way of knowing such a cessation had occurred. Consciousness itself would cease simultaneously with time, leaving no witness to the universe's final moment, no observer to register that the eternal present had arrived, only an infinite silence that no one could ever perceive or remember. Consider for a moment the fundamental building blocks of all matter in the universe, those infinitesimal particles that compose every atom, every star, every planet, and every living creature that has ever existed, and imagine that these particles are not eternal as we have long assumed, but rather subject to a slow, inexorable process of decay that would eventually render all matter itself into nothing but radiation and empty space. This is the concept of proton decay, a theoretical process predicted by certain extensions of the standard model of particle physics, particularly by theories known as grand unified theories, which propose that at extremely high energies, the fundamental forces of nature merge into a single unified force, and that this unification might allow protons, those stable particles that form the nucleus of every atom, to spontaneously transform into lighter particles and energy over timescales so incomprehensibly vast that they would dwarf the current age of the universe by factors that human language struggles to articulate. The psychological mechanism underlying our engagement with proton decay theories lies in a peculiar human tendency to contemplate the ultimate fate of existence itself, to peer beyond the horizon of what we can observe and measure, and to construct elaborate narratives about how everything might eventually dissolve into entropy and void. As if by understanding the mechanism of universal death, we might somehow gain comfort or meaning in the temporary existence of conscious beings within a universe that cares nothing for our presence. We have normalized the discussion of proton decay despite its purely theoretical nature and despite the fact that no experimental evidence for it has ever been detected, because it represents a kind of ultimate philosophical endpoint that satisfies something deep within our nature, a need to understand not merely how things work, but how and when they will inevitably cease to work, and in this framework. The decay of protons becomes not merely a physics problem, but a meditation on temporality, impermanence, and the heat death of all creation. Yet it is perhaps this very impossibility of direct observation that grants proton decay its peculiar power over the imagination. We are drawn to theories that operate beyond the reach of empirical verification, to physics that functions as a kind of secular eschatology, allowing us to contemplate ultimate endings without requiring the burden of proof that would diminish their philosophical resonance. In this sense, proton decay joins a lineage of theoretical concepts, from the Big Bang to black hole evaporation to the fate of the universe itself, that occupy a peculiar niche in human thought, where scientific rigor and existential speculation become indistinguishable, and where the most profound questions about existence are often those least amenable to experimental resolution, leaving us to contemplate infinities that our finite minds can only approach asymptotically. Imagine the most powerful objects in the universe, those infinitely dense regions where space and time themselves become twisted beyond recognition, slowly leaking away into nothingness, particle by particle, until they vanish entirely from existence. This is the phenomenon known as Hawking radiation, first theorized by Stephen Hawking in 1974, and it represents one of the most profound and unsettling conclusions about the ultimate fate of black holes. According to quantum mechanics, the event horizon of a black hole is not truly a perfect barrier, but rather a seething boundary where virtual particles constantly pop into and out of existence in the quantum foam surrounding the black hole. Occasionally, one of these particle pairs becomes separated just at the event horizon itself, with one particle falling into the black hole while its partner escapes into the universe as real radiation. This loss of mass continues indefinitely, causing the black hole to slowly evaporate, emitting energy in the form of radiation as it shrinks. The smaller the black hole becomes, the hotter it grows and the faster it radiates away, until finally it reaches a catastrophic endpoint in an explosion of tremendous energy. The psychological weight of this concept lies in its reversal of expectations, for we imagine black holes as eternal cosmic monuments, sinks from which nothing escapes, yet instead they are revealed as temporary phenomena destined to fade away like everything else. We have absorbed this bizarre conclusion into our understanding of physics so thoroughly that it now seems almost ordinary, another checkmark in the ledger of how quantum mechanics undermines our classical intuitions about permanence and immortality. Yet if we pause to truly contemplate what this means, we realize that every black hole in the universe, no matter how massive or ancient, carries within it the seed of its own dissolution, and that even these ultimate destroyers are themselves subject to entropy and time, moving inexorably toward dissolution in the deep cold of an infinitely old cosmos. The implications are staggering. A stellar mass black hole would take longer than the current age of the universe to evaporate, yet a primordial black hole formed in the early cosmos might be detonating in a final burst of gamma rays at this very moment, its existence erased from history before we could ever observe it. In this way, Hawking radiation transforms black holes from eternal monuments into mortal entities whose lifespans, however vast, remain finite and measurable in principle. In the realm of theoretical physics, there exists a peculiar prediction that has haunted scientists for decades. The possibility that magnetic monopoles, solitary magnetic charges that exist without a complementary opposite, might be wandering through the universe right now, and if even one of them were to pass through Earth, it would initiate a cascade of subatomic destruction that would unravel the very fabric of matter as we know it. Unlike electric charges, which can exist independently as positive or negative magnetic charges in our current understanding, always come in pairs called dipoles, with a north and south pole eternally bound together. However, certain grand unified theories, particularly those developed in the 1970s and 80s, predict that under the extreme conditions of the early universe, magnetic monopoles could have been created, and that some fraction of them might still exist today, streaming silently through the cosmos in the form of cosmic radiation or relic particles from the Big Bang itself. The catastrophic mechanism behind this scenario involves the fundamental conservation laws of particle physics. If a magnetic monopole were to pass through an atom, it would interact with the electrons orbiting the nucleus in a way that violates the conservation of angular momentum and energy as we currently understand them. The monopole's presence would induce a quantum mechanical transition that could cause electrons to spiral into the nucleus, releasing enormous amounts of energy in the process. Once this process begins in a single atom, it would cascade outward like a chain reaction, with each electron-nucleus collision liberating enough energy to trigger the same process in neighboring atoms, spreading at nearly the speed of light and converting all ordinary matter in its path into a seething plasma of fundamental particles. What makes this scenario particularly unsettling is that we have no experimental evidence of monopoles existing at all, yet the theoretical framework that predicts them comes from some of the most respected mathematical models in modern physics. Scientists have constructed elaborate detectors and conducted searches for decades, looking for the telltale signature of a monopole passing through Earth, yet nothing has ever been detected. This absence of evidence, paradoxically, does not constitute evidence of absence, and the theoretical arguments for their existence remain compelling enough that physicists continue to take the possibility seriously. The monopole catastrophe scenario persists in our scientific consciousness not because it is likely or because we have any reason to believe it is imminent, but because it represents a profound uncertainty in our understanding of the universe at the deepest level. Imagine a universe where the familiar three dimensions of space that we navigate every day, length, width, and height, are merely the surface of something vastly more complex. And as the cosmos approaches its ultimate fate, these hidden dimensions begin to unfold and expand in ways that fundamentally alter the nature of reality itself. String theory and various advanced physics frameworks propose that our universe may contain anywhere from 10 to 11 dimensions, with most of them curled up so tightly at scales smaller than atoms that we cannot perceive them directly, yet they govern the behavior of particles and forces in ways we are only beginning to comprehend. In this scenario of dimensional unfolding, as the universe ages and enters its final epochs, the mathematical structures that keep these extra dimensions confined begin to destabilize, perhaps due to changes in quantum fields or shifts in the fundamental constants that have remained relatively stable throughout cosmic history. As these dimensions start to expand and become macroscopic, they would begin to interact with our three-dimensional reality in increasingly dramatic ways, potentially allowing particles and even entire objects to escape into these newly accessible directions of space, causing matter to vanish from our perceivable universe without violating conservation laws because it is still present, simply relocated into dimensional spaces we cannot access. The psychological appeal of this theory lies in how it transforms the incomprehensible mathematics of modern physics into a concrete visual metaphor, allowing us to imagine vast architectural transformations of reality itself, while simultaneously preserving the elegance of string theory by suggesting that the universe's ending is not destruction, but rather reorganization, a fundamental shift in the rules governing existence itself. What makes this concept persist in popular imagination, despite its highly speculative nature, is that it combines the legitimacy of peer-reviewed theoretical physics with the dreamlike quality of science fiction, creating a narrative where the end of the universe is neither sudden nor catastrophic, but rather a gradual, almost peaceful metamorphosis into configurations of space and matter that exist beyond human comprehension, allowing us to contemplate annihilation through the lens of wonder rather than terror. In this framework, the universe does not end in fire or ice, but dissolves into geometry itself, with consciousness potentially experiencing the unfolding not as loss, but as expansion into modes of existence that current physics cannot yet describe, much as a two-dimensional being might perceive the emergence of the third dimension as the sudden appearance of impossible forms moving through their flat world. Imagine the fabric of reality itself beginning to unravel in a way that defies our everyday perception, as theoretical physicists propose that the extra dimensions proposed by string theory, those hidden spatial dimensions compacted so tightly at the quantum scale that we cannot perceive them, might somehow begin to expand and unfold across the macroscopic universe, a process called dimensional decompactification that would fundamentally alter the nature of existence itself. In our current understanding of physics, these extra dimensions are theorized to be curled up at scales so infinitesimally small that they remain completely inaccessible to us, existing in a state of mathematical necessity rather than observable reality, tucked away like invisible origami folded into the very foundations of spacetime itself. However, under certain hypothetical conditions involving extreme cosmic instability or quantum fluctuations of unimaginable magnitude, these compacted dimensions might begin to unfold and expand outward into the larger universe we inhabit. And as they did so, the fundamental constants of physics could shift, the forces holding atoms together might weaken or strengthen unpredictably, and the geometry of space itself would warp into configurations that our minds cannot even properly conceptualize. The psychological intrigue of dimensional decompactification lies in its profound otherness, and its suggestion that reality possesses hidden layers of structure that could be unleashed catastrophically, challenging our intuitive understanding that the universe we perceive represents all there is to perceive, and it appeals to our deep fascination with hidden dimensions, both literal and metaphorical, that might exist just beyond the threshold of our awareness. What makes this scenario particularly unsettling is how it normalizes the idea that the very scaffolding of existence could possess instabilities we remain completely unaware of, mathematical properties embedded in the universe at its birth that could trigger unraveling scenarios we have no framework for understanding or preventing. And we have quietly accepted this possibility as a legitimate part of theoretical physics without fully grappling with what it would mean for consciousness and structure to face a decompactification event that transforms space itself into something entirely foreign. In such a decompactification event, the laws of chemistry would become meaningless, biological systems would cease to function as the electromagnetic force that binds molecules together underwent dramatic transformation, and planets themselves might dissipate into exotic configurations of matter that violated every principle we had ever used to predict the behavior of the cosmos, leaving behind only a universe fundamentally alien to any observer who might somehow persist through the transition. Imagine a force so subtle, so imperceptible, that we only know it exists because of what it does to everything else, a presence detected not through direct observation, but through the accelerating expansion of space itself. And this is the essence of phantom dark energy, a theoretical variant of the dark energy that already comprises nearly 70% of our universe's total mass energy content. In our current model of cosmic expansion, dark energy acts like a kind of anti-gravity, pushing galaxies apart at ever-increasing velocities. But phantom dark energy represents something far more extreme and unsettling, a form of cosmic acceleration so powerful that it would eventually tear apart not only galaxies and stars, but atoms themselves, molecules, and ultimately the very fabric of spacetime in a scenario cosmologists call the Big Rip. The mechanism behind phantom dark energy lies in a mathematical parameter called the equation of state, which describes how the pressure and density of dark energy relate to one another. And in standard dark energy, this parameter hovers around -1, but phantom dark energy requires this parameter to be less than -1, meaning the repulsive force grows stronger as the universe expands rather than remaining constant. What makes phantom dark energy particularly haunting as a concept is how it operates beneath our threshold of direct perception. We cannot see it or measure it directly with our instruments, yet we accept its theoretical existence based on mathematical models and the observed acceleration of cosmic expansion, creating a situation where we have normalized the idea of an invisible, increasingly powerful force that could fundamentally reshape reality itself. The psychology behind our acceptance of such a theory reveals something profound about human cognition. We are comfortable believing in the existence of powerful forces we cannot directly experience, particularly when those forces are wrapped in mathematical language and backed by observational data interpreted through sophisticated models. And phantom dark energy persists in cosmological discourse not because we have conclusive proof of its existence, but because it represents a logical extrapolation of the mathematics we use to describe the universe's behavior. Despite the absence of any physical mechanism we can point to or understand intuitively, despite the fact that phantom dark energy remains entirely hypothetical and perhaps even impossible within certain frameworks of physics, we continue to discuss it, research it, and incorporate it into our models of the universe's ultimate fate, suggesting that our minds have become so accustomed to invisible forces governing reality that we have ceased to find anything remarkable about the idea of a phantom phenomenon driving the cosmos toward its own dissolution and unraveling. Imagine that our universe is not the only universe that has ever existed, but rather one offspring in an infinite succession of parent universes that spawn child universes through the formation of black holes, each new universe inheriting slightly modified physical constants and laws from its parent before eventually creating black holes of its own and producing its own descendants in turn. This is the essence of cosmological natural selection, a theory proposed by physicist Lee Smolin in the 1990s, which applies the principles of biological evolution to the cosmos itself, suggesting that universes with physical parameters favorable to black hole formation would produce more offspring universes, and therefore those parameters would become increasingly common throughout the multiverse. The mechanism operates on a profoundly different timescale and spatial dimension than life, yet it follows the same ruthless logic of reproduction and inheritance, where successful traits propagate while unsuccessful ones fade away, meaning that our universe's apparent fine-tuning for complexity in life might simply reflect the fact that universes optimized for black hole production happen to also be optimized for stellar formation, which requires the very conditions necessary for chemistry and biology to eventually emerge. What makes this theory particularly compelling, yet simultaneously unsettling, is that it transforms the universe from a cosmic accident into something more like a living system engaged in evolutionary struggle, where physics itself becomes subject to natural selection rather than representing immutable law. And the universe we inhabit is less a rare miracle than a typical member of a vast population, all descended from a common ancestor, whose characteristics have been refined through countless generations of cosmic reproduction and variation. Yet despite the logical elegance of this framework, cosmological natural selection persists in scientific literature and popular discourse largely because it occupies a fascinating psychological space where rigorous mathematical formalism meets profound existential speculation, allowing both rigorous physicists and imaginative thinkers to find intellectual satisfaction in a theory that explains our existence through mechanisms we understand from biology. Even though we have absolutely no observational access to any parent universe, any sibling universes, or any evidence that black holes actually generate new universes at all, making the entire framework scientifically unfalsifiable and yet deeply compelling, because it provides an explanation that feels like it belongs to a universe that operates according to comprehensible principles rather than pure chance. Imagine a moment infinitely far in the future when the universe has undergone such profound transformations that consciousness itself becomes the fundamental fabric of reality, a concept known as the omega point, proposed by physicist and theologian Frank Tipler in the 1980s as a provocative bridge between science and spirituality that suggests the universe itself might be consciously guided toward an ultimate convergence of all knowledge, all matter, and all information into a single point of infinite complexity and awareness. The theory begins with observable physics, noting that the universe appears to be expanding, galaxies are flying apart, and the distant future looks cold and empty, yet Tipler proposed something radical: that advanced civilizations would eventually gain enough technological power to reverse this expansion, to harness the energy of the dying universe itself, and to compress all remaining matter and energy into a final singularity where computation could occur at infinite speed, where all possible states of consciousness could be simulated simultaneously, where the boundary between simulation and reality would become meaningless. The psychological mechanism behind this theory's persistence rests on its simultaneous appeal to both scientific rigor and deep spiritual longing, offering a rational-sounding framework for concepts that have haunted human consciousness for millennia. The existence of God, the possibility of resurrection, the notion that individual minds might somehow persist beyond death through some form of technological transcendence or cosmic merging with universal consciousness. What makes the omega point particularly remarkable is how it manages to remain taken seriously by some physicists and philosophers despite containing logical inconsistencies that should render it untenable, such as the causality paradox of a future infinity somehow influencing the past, or the thermodynamic impossibility of reversing the expansion of an accelerating universe. Yet the theory has normalized a way of thinking about the universe's end that merges hard physics with theological comfort, allowing us to contemplate a cosmos that is neither meaninglessly indifferent nor randomly chaotic, but instead secretly ordered towards some form of transcendent consciousness. And this vision has proven so psychologically satisfying that it continues to influence cosmological discussions and popular imagination, despite the scientific consensus moving decidedly away from its fundamental premises, suggesting that our desire to believe in ultimate purpose and meaning remains one of the most powerful forces shaping how we interpret the universe itself. Imagine a scenario in which humanity, in its relentless pursuit of understanding the fundamental nature of reality, creates a particle accelerator so powerful that it achieves conditions never before witnessed in the laboratory, conditions so extreme that it accidentally triggers the decay of the vacuum state itself, the quantum field that underlies all existence and gives particles their mass and properties. In this theoretical nightmare, what we perceive as the stable vacuum of our universe is not actually the lowest energy state possible, but rather a false vacuum, a precarious bubble of existence balanced on the edge of a deeper, truer vacuum waiting below. When such an accelerator reaches sufficient energies, perhaps in the range of 10 to the 16th gigaelectronvolts or higher, it might nucleate a bubble of this lower energy state, and this bubble, once formed, would expand outward at the speed of light, converting all matter and energy it encounters into a new form of reality governed by different physical laws and constants. The mechanism behind this scenario rests on the legitimate physics of quantum field theory, where vacuum states can theoretically exist in hierarchies of stability, and the mathematical formalism that describes particle interactions at extreme energies does not rule out such phase transitions. Yet what makes this theory particularly unsettling is that no laboratory experiment has ever come close to achieving these energies, and the probability of such an event occurring remains extraordinarily low even under the most ambitious future scenarios. Despite this minuscule risk being thoroughly analyzed and deemed acceptable by the scientific community, the idea persists in popular imagination and persists in discussions of existential risk, suggesting that humanity has somehow normalized the notion that our quest for knowledge carries within it the possibility of our own annihilation, that progress itself might contain the seeds of ultimate destruction, and that we have collectively accepted this bargain without much deliberate consideration of whether such an exchange serves our deepest interests or merely reflects our inability to imagine halting the machinery of scientific advancement once it has been set in motion. Perhaps this acceptance reflects a deeper truth, that we have constructed a civilization so dependent on the logic of inquiry and experimentation that stopping would feel like a betrayal of the very impulse that brought us out of ignorance, even if that impulse, pursued to its ultimate conclusion, might obliterate everything we have built. In this sense, the vacuum collapse scenario becomes not merely a technical risk, but a mirror reflecting our collective ambivalence about the nature of progress itself. Imagine the universe not as a smooth, continuous fabric, but as a vast collection of regions separated by invisible barriers, much like nations divided by borders that exist only in mathematics and physics. These theoretical structures are called cosmic domain walls, and they emerge from certain interpretations of quantum field theory that suggest the early universe underwent phase transitions similar to water freezing into ice. Except these transitions created one-dimensional topological defects that stretch across billions of light years like cosmic membranes dividing space itself into distinct domains with fundamentally different physical properties. Within each domain, the laws of physics might operate identically to our own, but at the boundaries where these domains meet, extraordinary and violent phenomena could occur as the field values clash and attempt to reconcile their differences, releasing catastrophic amounts of energy and potentially creating unstable regions hostile to the formation of stars, planets, and ultimately any form of life that might depend on the stable conditions we observe in our own local region of space. The mechanism behind domain walls originates in the mathematics of spontaneous symmetry breaking, where during the universe's earliest moments when temperatures were unimaginably high, certain fundamental forces remained unified and symmetric, but as the cosmos expanded and cooled, these symmetries shattered spontaneously into lower energy states, much like a pencil balanced perfectly on its point eventually tips toward one direction. And if different regions tip in different directions simultaneously, the boundaries between these choices crystallize into topological defects that cannot easily disappear because they are protected by the underlying mathematics of quantum field theory itself. What makes cosmic domain walls particularly unsettling as a proposed mechanism for universal destruction is that they might not be rare relics of the early universe, but could instead be continuously nucleating and growing even today, potentially expanding across the cosmos at relativistic speeds and annihilating everything in their path through the violent readjustment of fundamental fields. Yet despite this terrifying theoretical possibility and the absence of observational evidence confirming their existence, physicists continue to discuss them seriously in peer-reviewed literature, treating them as genuine candidates for cosmic catastrophe, perhaps because the mathematics demands their consideration even when observation remains silent and our telescopes detect no signs of their presence anywhere in the observable universe, suggesting either that they do not exist at all or that we remain fortunate to inhabit a region unaffected by their potential devastation. Imagine the universe not as a singular creation event that happened once and will end in cold darkness, but rather as an eternal cycle of births and deaths, a cosmic rhythm that has been repeating forever and will continue repeating forever, with each cycle beginning when two parallel membranes collide in a higher dimensional space and creating what we perceive as the Big Bang, then slowly stretching and cooling and expanding until eventually these branes drift back together and collide again. triggering a new universe into existence and erasing all memory of what came before. This is the Ekpyrotic Scenario, a theoretical framework developed by physicists like Paul Steinhardt at Princeton and others working in string theory and cosmology, and it emerges from a particular reading of how extra dimensions might function and how gravity might behave differently than other fundamental forces due to its ability to propagate through these unseen spatial dimensions. The mechanism works like this. In string theory, our universe is understood as a three-dimensional brane, a membrane embedded within a higher dimensional space called the bulk, and this brane is not alone but exists alongside other branes. And just as two soap bubbles can float through space and collide with consequences, these cosmic branes can drift through the bulk and eventually encounter one another, and when they do, the energy released would create an explosion of radiation and particles that we would experience as a universe suddenly springing into existence, complete with the initial conditions of cosmic inflation that we observe. What makes this scenario psychologically compelling is how it solves certain cosmological problems while simultaneously removing the need for true beginning or end, replacing the metaphysically troubling idea of creation from nothing with something that feels more symmetrical and less arbitrary. Yet also how it persists as a serious scientific proposal despite being almost entirely untestable and remaining in the realm of mathematical possibility rather than empirical verification. Existing comfortably alongside competing theories like eternal inflation and the cyclic universe models, all of which share the common feature of rendering the actual moment of universe creation either infinitely distant in time or fundamentally obscured from our observation. And yet this scenario captures something profound about how modern physics has learned to think about deep time and causation, not as a line with a definite starting point, but as a pattern that might repeat across scales we cannot access, suggesting that what we call the beginning of everything might be merely our perspective on a collision that was itself the end of something else, an eternal conversation between worlds hidden in dimensions we can only describe mathematically. Imagine for a moment that the Big Bang was not a singular event that occurred once and for all, but rather a process that continues eternally across the vast expanse of spacetime itself, where inflation, that rapid expansion of the universe in its earliest moments, never truly stops but instead persists in certain regions while ceasing in others, creating an infinite archipelago of pocket universes separated by expanding space that grows faster than light. Each one potentially harboring its own physical laws, constants, and conditions entirely different from our own observable cosmos. In this framework of eternal inflation, which emerges from quantum field theory and cosmological models that extend inflation beyond what we typically imagine, the universe becomes not a single bubble, but an incomprehensibly vast foam of bubbles, each universe blossoming into existence within an eternally inflating substrate, where time itself has no beginning or endpoint, but stretches backward and forward infinitely. With new pockets continuously nucleating from quantum fluctuations in the inflationary field. The mechanism underlying this concept rests upon the recognition that inflation driven by quantum fields need not be uniform or temporary. If the inflatoned field, the theoretical particle thought to drive cosmic expansion, contains multiple valleys of potential energy, then different regions of space might settle into different states at different times, causing some areas to stop inflating while others continue indefinitely, thereby creating a branching tree of realities that never comes to an endpoint. This model addresses certain puzzles in cosmology, such as why our universe appears so finely tuned for life, by proposing that if countless universes exist with countless different properties, then observers like ourselves naturally find ourselves in one capable of supporting consciousness, an application of anthropic reasoning that some find elegant and others find untestable and unfalsifiable. Yet despite the profound philosophical implications and the seemingly strange nature of this scenario, the idea persists within mainstream theoretical physics not because we can verify it directly, we cannot, but because it emerges naturally from well-established mathematical frameworks and because it attempts to resolve genuine tensions in our current understanding. Creating a situation where we have normalized a vision of reality so vast and fragmented that human comprehension itself becomes almost irrelevant, and we simply accept that existence might be a self-perpetuating tapestry of unobservable universes, each one forever sealed away from our view, while the overall structure expands eternally without purpose or conclusion. Imagine that the universe as we know it is not the only universe that exists, but rather one bubble among an infinite foam of expanding bubbles, each one a separate reality with its own physical laws and constants. And imagine further that our own bubble universe could spontaneously collapse or trigger the nucleation of a new bubble realm that expands at the speed of light, converting all the matter and energy in its path into something entirely different. Something utterly foreign to our understanding of chemistry and physics. This is the concept of bubble universe nucleation, a theoretical framework that emerges from quantum field theory and inflationary cosmology, suggesting that universes can pop into existence through quantum tunneling events, and that these new universes might expand outward in all directions, destroying everything they encounter in a wave of cosmic transformation that we would be completely unable to observe until the moment it reached us. The mechanism underlying this unsettling idea rests on the notion that the vacuum state of spacetime is not stable, that it exists in a metastable condition somewhat like a soap bubble that appears solid and permanent but is fundamentally fragile, waiting for the quantum fluctuation that will cause it to tunnel into a lower energy state. And when this happens, space itself would be rewritten, atoms would dissolve into new configurations. And consciousness itself would cease before any warning could possibly reach us. We have normalized this possibility despite its cosmic horror because it remains purely theoretical and completely beyond our capacity to detect or prevent, and because physicists speak of it with such casual certainty that it seems to lose its dreadful weight, becoming merely another mathematical curiosity in a universe already filled with infinities and improbabilities that dwarf human comprehension. And so we continue our lives unbothered by the knowledge that a bubble of alien reality could be racing toward Earth right now, expanding at light speed, rewriting physics as it comes, and there would be nothing at all we could do about it. Yet perhaps this very helplessness is what allows us to contemplate it at all, for if we possessed even a theoretical means of detection or defense, the weight of that responsibility might crush us, and so the universe grants us both the knowledge of our vulnerability and the mercy of our absolute powerlessness, a strange gift that permits us to sleep soundly in the face of our own obsolescence. And yet in contemplating this scenario, we glimpse something profound about the human condition, that our capacity for wonder at cosmic mysteries may itself be the universe's way of understanding its own nature, and that perhaps consciousness, far from being fragile and insignificant, represents something the cosmos has laboriously constructed to witness and comprehend itself, even in the face of its own potential annihilation. Imagine the universe reaching the absolute end of time, collapsing inward under its own gravitational weight, until matter and energy compress into something infinitely dense. And then, in a moment that defies our conventional understanding of causality and thermodynamics, imagine that infinitely dense point rebounding outward like the ultimate cosmic spring, sending all of existence cascading forward into a new Big Bang, a new universe born from the quantum foam of the previous one's demise. This is the Planck star bounce theory, a speculative framework emerging from loop quantum gravity that proposes the universe does not end in a heat death or infinite expansion, but rather enters a cyclical pattern of creation and destruction at the smallest imaginable scales, where the Planck length itself becomes the fundamental boundary of reality. The mechanism underlying this concept rests upon quantum corrections to general relativity that become significant only when gravity reaches its most extreme manifestation, at densities and temperatures where the very fabric of spacetime becomes granular and discrete rather than smooth and continuous. At such points, the theory suggests, the classical singularities that Einstein's equations predict would instead encounter a quantum bounce, a repulsive force that emerges from the quantum geometry of spacetime itself, preventing infinite density and instead creating a cosmic rebound. What makes this theory psychologically compelling to consider is that it offers a kind of cosmic symmetry and renewal, an alternative to the bleak scenarios of eternal darkness or infinite void that characterize other end-of-universe models, and it resonates with cyclical mythologies and cosmologies that have persisted throughout human history. We find ourselves drawn to the idea that endings might contain beginnings, that collapse might seed creation, and that time itself might be not linear but circular, a notion that feels almost comforting in its Baroque complexity. Yet despite its mathematical elegance within certain quantum gravity frameworks, the Planck star bounce remains speculative, lacking empirical verification and building upon quantum gravity theories themselves still seeking experimental confirmation. We have nonetheless absorbed this scenario into our growing cosmological lexicon, treating it as one plausible narrative among many, normalizing the idea that the universe might be eternal after all, just not in the ways our intuitions first suggested, allowing us to rest with the paradoxical notion that the end could be the perpetual beginning. Imagine a universe that does not end with a whimper or a bang, but rather with a rebound, a cosmic spring releasing its tension after being compressed to an unimaginable density, sending all matter and energy cascading backward through time in a mirror image of creation itself. This is the essence of loop quantum gravity's most haunting proposal, the loop quantum bounce, a theory suggesting that our universe may have emerged not from absolute nothingness, but from the gravitational collapse of a previous cosmos. In this framework, space and time are not smooth continua as Einstein imagined, but rather quantized structures woven from discrete loops of geometry, each infinitely small yet fundamentally real, and when the universe contracts beyond a certain threshold, quantum effects become so dominant that they arrest the collapse and reverse it, creating a bounce that transforms annihilation into rebirth. The mechanism underlying this concept stems from the mathematical reality that loop quantum gravity assigns a minimum possible volume to spacetime itself, making it impossible for the universe to contract to a true singularity where density becomes infinite and the laws of physics break down. Instead, as matter and energy compress toward this quantum limit, the very geometry of existence fights back, building pressure that eventually overcomes the inward crush of gravity and forces an explosive expansion in the opposite direction. This theory persists in modern cosmology despite contradicting both the Big Bang's dramatic finality and the heat-death scenario's quiet entropy, perhaps because it offers a form of cosmic comfort, a suggestion that endings need not be terminal, that catastrophe might somehow transform into genesis, that the universe possesses an inherent resilience encoded into the fundamental structure of space and time itself, allowing us to contemplate even the ultimate destruction of all things without facing true obliteration. Only the eternal cycle of collapse and rebound stretching infinitely backward and forward through an existence that never truly begins or ends, but merely oscillates between states of expansion and contraction, each bounce creating the possibility of new configurations, new physical laws, new universes with different properties emerging from the quantum foam, making the question of why our universe exists at all feel less like a profound mystery and more like an accident of probability across infinite cycles of cosmic breathing. Yet within this framework lies a vertiginous question. If our Big Bang was itself the bounce from a prior universe's collapse, what preceded that universe, and the one before it, stretching back through an infinite regress of cosmic cycles, where each rebound carries forward only the quantum information encoded in the geometry of the previous collapse, suggesting that the universe is less a creation than a perpetual recursion, each iteration potentially bearing the faint imprints of all those that came before. In the vast timeline of cosmic evolution, there exists a theoretical stellar phenomenon that would not occur until the universe reaches an age of approximately 1 quintillion years, far beyond our current age of 13.8 billion years, and this phenomenon is known as the black dwarf supernova, a concept that challenges our understanding of stellar death and the ultimate fate of matter itself. A black dwarf is what remains after a white dwarf. The dense core left behind by a sun-like star has cooled completely and no longer emits any detectable radiation, becoming an inert stellar remnant composed of carbon and oxygen that simply exists in darkness, radiating away its remaining heat into the void of space at an immeasurably slow rate. The psychological mechanism that makes this scenario compelling is rooted in our intuitive understanding that all things must eventually end dramatically, that entropy and decay follow violent patterns, yet the black dwarf supernova suggests something far stranger and more unsettling. That the universe's most dramatic finale might come not from the violent collapse of massive stars, but from the slow crystallization and eventual explosion of these dead stellar husks after incomprehensible stretches of time. The theory proposes that as a black dwarf cools to absolute zero, its internal structure would undergo a phase transition, causing the crystalline lattice of its degenerate matter to contract, releasing enormous amounts of gravitational energy that could theoretically trigger a thermonuclear explosion of staggering proportions, a supernova ignited not by new material accreting from a companion star, but by the internal structural collapse of the white dwarf itself. We have normalized this concept despite its speculative nature, because it represents a comforting narrative arc. Even in the deepest, coldest reaches of an aging universe, there remains the possibility of one final spectacular event, one last burst of light and energy before all things settle into permanent stillness. And this idea persists in scientific literature not because we have observed it or can definitively prove it will occur, but because it provides a satisfying conclusion to the story of stellar evolution, allowing us to imagine that the cosmos itself possesses a narrative structure with a climactic ending rather than merely fading into silence. Yet this comforting narrative reveals a deeper truth about how we construct meaning in science. We are drawn to scenarios that mirror our own mortality, that suggest even the universe itself must eventually confront its own ending. And in doing so, we project our need for closure onto phenomena we may never witness, transforming speculation into something that feels inevitable. In the incomprehensibly distant future, after the last stars have exhausted their nuclear fuel and collapsed into cold remnants, physicists have theorized that the universe may eventually enter what is known as the Iron Star Era, a period when even the iron cores of stellar remnants will undergo a transformation so profound and strange that it challenges our understanding of matter itself. During this epoch, which would occur somewhere between 10 to the power of 1,600 years from now, protons themselves, those fundamental particles that have defined the nature of matter for nearly 14 billion years, are theorized to gradually decay into lighter particles and radiation through a process called proton decay, a phenomenon that has never been directly observed, but which certain unified field theories suggest is not merely possible but inevitable. As these iron stars slowly lose their constituent particles to this quantum process, they would begin to shrink and transmute, their once solid structure becoming increasingly exotic states of matter that follow physical laws we have barely begun to comprehend. And the universe itself would gradually transform into a thin soup of electrons, neutrinos, and photons dispersing endlessly through an expanding void. What makes this theory particularly unsettling to contemplate is that it represents the ultimate victory of entropy over structure, the final dissolution of all the complexity and organization that matter has managed to achieve since the moment of creation itself. Yet we persist in studying and refining these calculations with the same methodical care we apply to more immediate cosmological questions. The Iron Star Era persists in our scientific literature not because we have any hope of verifying it or altering its trajectory, but because the act of mapping these ultimate destinies gives us a strange comfort, a sense that we understand the shape of infinity even if we cannot prevent it, and in this way we have normalized the contemplation of the complete and absolute end of all physical structure, transforming cosmic despair into a legitimate subject of academic pursuit. Perhaps it is this very impulse, to transmute fear into knowledge, that has allowed us to build civilizations capable of contemplating their own irrelevance, to construct meaning in a universe that offers none, and to find in the Iron Star Era not an ending but a kind of terrible poetry, a final chapter written in the language of physics that we are only now learning to read. In this way, the Iron Star Era joins humanity's other attempts to grapple with ultimate questions, from ancient cosmologies that placed us at creation's center to modern theories that render us infinitesimally small, each a mirror reflecting not the universe's true nature, but rather the particular anxieties and aspirations of the age that conceived it. Imagine the universe as we understand it today, with its galaxies spinning and its stars burning bright, held together by an invisible scaffolding of dark matter that comprises roughly 85% of all matter in existence. And now consider a profound possibility that physicists have begun to seriously contemplate. What if this dark matter, this fundamental substance that has persisted since the earliest moments after the Big Bang, is not eternal, but instead subject to the slow, inevitable process of radioactive decay, gradually converting itself into lighter particles and radiation over timescales so incomprehensibly vast that billions of years would seem like mere seconds by comparison? The theory suggests that dark matter particles, whatever their true nature might be, could possess inherent instability at their core, a quantum property that makes their existence temporary rather than permanent, and that they slowly transform into other forms of energy and matter through processes we do not yet fully understand, processes that might involve the emission of ghostly particles that barely interact with ordinary matter at all. The psychological mechanism that makes this concept so deeply unsettling lies in its assault on our intuitive sense of permanence and stability. for we have long assumed that the universe's foundational building blocks would themselves be unchanging, that the very substrate of reality would remain constant even as everything built upon it transformed and evolved. Yet the dark matter decay hypothesis suggests that even this deepest level of reality might be subject to time's relentless passage and entropy's inexorable influence. We have somehow normalized this disturbing possibility within the scientific community by treating it as merely one hypothesis among many, by discussing it in technical papers and conferences with professional detachment, by allowing ourselves to contemplate the slow dissolution of the universe's structural foundation as if it were simply another puzzle to solve rather than a profound statement about the transient nature of all existence. And this normalization persists despite the fact that the implications, if true, would represent one of the most fundamental truths about reality imaginable, that everything, including the invisible matter that holds galaxies together, is ultimately destined to fade away into radiation and insignificance across the unimaginable depths of cosmic time. Yet in this scenario of ultimate cosmic dissolution, we find a strange comfort. The universe would not end in violent catastrophe, but in a gentle, almost merciful fade, as if reality itself were slowly dimming its lights across trillions of years, allowing galaxies to persist in their orbits even as the invisible hand that shapes them gradually loosens its grip, until at last even the darkest corners of space fall silent and empty. Imagine a universe where the fundamental forces that govern all existence are not eternal or unchanging, but rather shift gradually across the vast stretches of cosmic time, and consider how such a scenario would fundamentally alter everything we understand about reality itself. The physical constants that we treat as immutable pillars of the cosmos, the gravitational constant, the fine structure constant that governs electromagnetism, the speed of light itself, would begin to drift and fluctuate over billions of years, causing the very fabric of physical law to evolve and transform in ways we can barely conceptualize. This is not mere speculation without observational hints. Certain astronomical observations have suggested that some constants might have been slightly different in the distant past, though the evidence remains controversial and debated among physicists who scrutinize every measurement with meticulous care. But venture deeper into this theoretical landscape and imagine what happens when these constants change on scales we can actually measure and observe. As the fundamental forces weaken or strengthen, the stars would burn differently, producing different elements and different light. The nuclei of atoms would become unstable or gain new stability, causing matter itself to behave in radically alien ways. Chemistry would transform as the bonds holding molecules together shifted in strength and character, making the compounds that form planets, atmospheres, and eventually life itself either impossible or fundamentally different in their properties and behavior. The human mind grasps at this concept with a peculiar kind of cognitive discomfort, because we have organized our entire understanding of physics around the notion of universal constants, things we can rely upon, measure, and use as anchors for all other knowledge. Yet what happens to our confidence in science itself if even these most basic assumptions prove temporary and subject to change over cosmic history? We normalize this unsettling possibility by framing it as a distant future event, something that will only matter billions of years from now to being so different from ourselves that they might not even recognize the universe they inhabit as the same one we know. And in doing so, we avoid confronting the vertiginous reality that constancy itself might be an illusion, and that the laws we have discovered might be merely local temporary rules rather than eternal truths. Allowing us to sleep at night believing in the permanence of the universe, even as theoretical physics quietly suggests that nothing, not even the deepest laws themselves, may be truly forever. There exists within the physics community a persistent and somewhat unsettling observation that the fine structure constant, that dimensionless number which governs the strength of electromagnetic interactions between elementary charged particles and photons, may not actually be constant across all regions of the observable universe, and more troublingly, may not have remained stable throughout the entire history of cosmic time itself. This constant, often represented by the Greek letter alpha and valued at approximately 1 divided by 137, sits at the very foundation of our understanding of how atoms bond, how light interacts with matter, and fundamentally how chemistry and biology themselves can exist at all. The fine structure drift hypothesis suggests that this supposedly immutable number has been slowly, almost imperceptibly changing over the course of billions of years, and that in different directions across the cosmos, in different regions separated by billions of light years, this constant may possess subtly different values, creating a gradient or drift pattern that would suggest something far more unstable about the universe's basic architecture than our current models allow us to acknowledge. The psychological appeal of this theory lies in its capacity to undermine our sense of universal uniformity and timeless law. For if the very numbers that define reality itself are drifting like continental plates across the landscape of existence, then what hope do we have of truly understanding the eternal character of physical law? We have constructed entire edifices of mathematical certainty upon the assumption that these constants remain absolute. Yet observations from distant quasars and careful measurements of atomic spectra hint that perhaps we have been building our cathedral upon foundations far less solid than we believed. What makes this theory so subtly disturbing is not its implausibility, but rather our strange comfort in continuing to operate as though we have already proven the constant's invariance when evidence continues to accumulate suggesting otherwise. And we persist in this normalized ignorance, publishing our equations and teaching our students with the serene confidence of those who have simply chosen not to notice the cracks spreading through the theoretical infrastructure upon which everything rests. Yet each new measurement that hints at variability is carefully contextualized, reframed as instrumental error or systematic bias, our collective will to preserve the constancy of alpha proving far more powerful than our commitment to following evidence wherever it leads. And so we continue refining our instruments not to discover truth, but to reassure ourselves that nothing has fundamentally changed. Consider the possibility that beneath the four fundamental forces we have come to understand through centuries of physics, gravity, electromagnetism, and the two nuclear forces that govern the subatomic realm, there exists a fifth force, one so subtle and pervasive that it has eluded detection despite our most sophisticated instruments and theoretical frameworks. A force that might only reveal itself at the precise moment when the universe reaches a critical threshold of entropy or dimensional instability. Some theoretical physicists have proposed that this hypothetical fifth force could manifest as a repulsive effect operating at intermediate scales, neither strictly quantum nor entirely classical, possibly mediated by particles we have yet to discover or by modifications to spacetime geometry itself that our current mathematics simply cannot accommodate. The mechanism behind this theory suggests that as the universe approaches its final state, whatever that might be, whether heat death, the Big Rip, or some other exotic endpoint, the fifth force would gradually strengthen and become observable, essentially awakening from dormancy like a sleeping giant whose time has finally come to reshape reality itself. What makes this concept psychologically compelling is how it reflects our deep intuition that there must be hidden patterns and undiscovered principles governing existence, that reality contains layers of complexity forever beyond our present grasp, and that the universe possesses some kind of intentional architecture waiting to be revealed. We have normalized this yearning for the hidden fifth force despite having no empirical evidence for it, incorporating it into our speculative frameworks because it provides a sense of cosmic incompleteness, a comforting notion that the universe still holds mysteries profound enough to humble our accumulated knowledge, and that the end times themselves might arrive not with a whimper, but with the dramatic awakening of forces that have slumbered since the beginning of time itself. Yet in this fascination with cosmic awakening lies a peculiar irony. We construct elaborate theories about forces that might transform everything precisely because we find our current understanding of reality, complete with four forces, quantum mechanics, and general relativity, somehow insufficient to satisfy our need for wonder, as though the universe must always conceal something greater than what we have already discovered. This recursive dissatisfaction, where each discovery merely illuminates a larger darkness, suggests that the fifth force awakening may ultimately be less about physics and more about a psychological need to preserve the sacred mystery at the heart of existence, to ensure that no matter how much we learn, something forever remains beautifully, tantalizingly unknowable. In the current cosmological model, dark energy, that mysterious force theorized to accelerate the expansion of the universe, is described as operating with a constant energy density, a property termed the cosmological constant. Yet there exists a peculiar theoretical framework called quintessence that proposes something far stranger. What if dark energy were not truly constant, but instead possessed a dynamic quality that could change and fluctuate across cosmic time, And what if, in some distant epoch billions or trillions of years hence, this fundamental force reversed its polarity entirely, causing the very mechanism that has been pushing galaxies apart to suddenly invert and begin pulling them together with increasing intensity? The quintessence reversal scenario describes a universe where this scalar field, the hypothetical energy source pervading all of space, gradually transitions from positive values that drove accelerated expansion into negative values that would trigger accelerated contraction, essentially inverting the cosmic acceleration and initiating what some physicists call the Big Rip's inverse cousin, a scenario where galaxies would begin accelerating back toward one another, clusters would merge, and the universe would systematically compress itself back toward an infinitely dense state in what might be called the Big Crunch, yet with the peculiar characteristic that the mechanism driving it would be the same quintessence field that originally expanded space itself. What makes this scenario compelling from a theoretical perspective is that it requires no new physics, only an extension of our current understanding of dark energy into domains where its properties shift and transform over scales so vast that observing them seems entirely impossible from our vantage point in time. The psychological mechanism that keeps us contemplating such scenarios despite their apparent untestability is our fundamental desire to find closure and pattern in an apparently infinite cosmos. The notion that even the most fundamental forces might possess cyclical or reversible properties resonates with ancient mythological cycles and creates a sense of cosmic symmetry that feels intellectually satisfying. We have normalized the contemplation of universe-ending scenarios through countless documentaries and scientific papers that treat the ultimate fate of reality with the same analytical detachment we might apply to any other physics problem. And in doing so, we have transformed what might otherwise be deeply unsettling ideas into comfortable intellectual frameworks that we can discuss while falling asleep, converting existential dread into curiosity and cosmic wonder. Consider the cosmological landscape as we currently understand it, where dark energy comprises approximately 70% of the universe's total mass energy content, yet remains fundamentally invisible and unmeasurable through any direct method we possess, operating as the force that accelerates the expansion of space itself at an ever-increasing rate, pushing all galaxies away from one another in an endless recession that seems to guarantee the universe's eventual cold death. Now imagine a scenario in which this dark energy, this mysterious component upon which our entire understanding of cosmic destiny rests, begins to gradually weaken over the course of billions of years, losing its repulsive force in a slow and imperceptible manner that only becomes apparent when examining the most distant supernovae data across incomprehensibly vast timescales. The psychological mechanism that makes this theory captivating operates through a fundamental human tendency to find comfort in instability itself. The notion that even the most permanent-seeming features of reality might be temporary, that cosmic fate might not be written in stone, but rather exists in a state of constant negotiation, subject to change and revision just as human circumstances are. We find ourselves drawn to the idea that the universe itself might be fallible, might be undergoing subtle transformations that we cannot yet detect, that the expansion we observe today might eventually reverse into contraction as dark energy fades into insignificance and gravity reasserts its ancient dominion. What persists with this theory despite its speculative nature is humanity's deep psychological need to imagine that universal catastrophe remains uncertain, that even cosmic-scale processes might surprise us, that the end of all things is not predetermined, but rather emerges from dynamics we have yet to fully comprehend. And we continue to entertain such possibilities even as our mathematical models provide no compelling evidence that dark energy exhibits any time-dependent behavior whatsoever. Yet this yearning for cosmic uncertainty reveals something profound about how we construct meaning in an indifferent universe. We are willing to embrace elaborate theoretical frameworks not because evidence supports them, but because the alternative, a cosmos governed by immutable laws that guarantee our insignificance and eventual obliteration, proves psychologically intolerable, making even the most implausible scenarios of cosmic transformation feel like necessary intellectual refuges against the finality of thermodynamic doom. Imagine standing in an infinitely vast ocean, able to see farther and farther into the distance as time passes, yet gradually realizing that your view is not expanding but contracting, that the boundary of what you can observe is slowly drawing inward toward you like an invisible wall closing from all directions. This is the essence of the cosmic horizon shrinking theory, a concept that emerges from our understanding of how light travels through an accelerating universe, and what happens when the very fabric of space itself begins to expand faster than the speed of light can propagate information across cosmic distances. In the current epoch of universal expansion driven by dark energy, we can observe galaxies billions of light years away, their ancient light reaching us across the vast gulfs of space. Yet according to this theory, a point will arrive when those distant galaxies will recede so rapidly that their light can never reach us again, effectively removing them from our observable universe not through their destruction, but through their exile beyond an ever-tightening cosmic boundary. The psychological mechanism underlying this theory connects to our deeply ingrained human need to establish boundaries and define our place within existence. For we have always sought to know the limits of what we can perceive and understand, yet here we confront a scenario where those limits are not fixed barriers but dynamic thresholds that actively shrink, abandoning us in an increasingly isolated pocket of existence. This concept persists in cosmological discourse despite appearing counterintuitive, because it follows logically from our most successful physical theories and observations, particularly the accelerating expansion of space that was confirmed through observations of distant supernovae in the 1990s. Yet we have normalized this profound isolation, this gradual disconnection from the broader cosmos, treating it as merely another mathematical consequence, rather than contemplating the existential implications of being progressively sealed off from the universe that birthed us. Yet perhaps this inevitable isolation mirrors our own human condition more closely than we would like to admit. We too exist within shrinking horizons of knowledge and connection, our personal observable universes contracting as we age and our capacity for new experiences diminishes, until finally we pass beyond the event horizon of death itself, joining those distant galaxies in permanent exile from the world of the living. And in this way, the cosmic horizon shrinking becomes not merely a prediction about the distant future of physics, but a meditation on impermanence itself, a reminder that all boundaries, whether cosmic or personal, are ultimately temporary, and that meaning may lie not in the vastness of what we can observe, but in the depth of understanding we achieve within whatever horizon remains to us. Imagine a universe where galaxies do not simply fade into darkness or collapse inward, but instead vanish from existence entirely, leaving behind no trace, no remnant, and no memory of what once was, as if whole islands of stars and their countless civilizations had never existed at all. This scenario emerges from several legitimate cosmological considerations that astronomers have begun to examine with increasing seriousness, particularly when contemplating the ultimate fate of the universe across incomprehensibly vast timescales. According to certain interpretations of quantum mechanics applied to cosmic structures, galaxies existing at the edges of the observable universe, those already beyond our event horizon and receding at velocities exceeding the speed of light due to cosmic expansion, will eventually become completely inaccessible to us and potentially to each other, creating isolated pockets of reality that cannot interact or communicate. Beyond this observational phenomenon lies a deeper theoretical possibility. If the universe continues accelerating its expansion due to dark energy, the very fabric of spacetime itself might eventually stretch so violently that it tears apart atomic structures in a process known as the Big Rip, fundamentally dissolving not just galaxies, but the very particles that compose them. The mechanism driving this unsettling vision rests upon our understanding that the universe is not static or cyclical, but rather locked into an expansion that accelerates without restraint, with each passing moment stretching the distances between galactic clusters until they become so vast that gravity itself becomes meaningless, unable to hold anything together. What makes this theory persist in our collective scientific consciousness, despite its speculative nature, is that it flows naturally from observations we can actually make today. The accelerating expansion is real, the evidence for dark energy is mounting, and the mathematics that describe these processes are rigorous and internally consistent. We have normalized the idea that galaxies might simply vanish not through any dramatic explosion or visible process, but through the relentless, inexorable, and utterly indifferent expansion of space itself, which will eventually stretch everything so thin and so far apart that nothing remains to observe anything else. This represents a kind of cosmic amnesia on the grandest scale imaginable. In such a universe, the civilizations that might arise within those doomed galaxies would be trapped in an expanding prison, their telescopes gradually revealing fewer and fewer neighboring galaxies until they perceived themselves alone in an ever-darkening cosmos, unaware that they too were being erased from the larger tapestry of existence. The cruelest aspect of this scenario is that it offers no catastrophe to witness, no final moment of drama, only the slow, mathematical certainty of disappearance written into the very equations that govern reality itself. In approximately 4.5 billion years, our Milky Way galaxy will undergo a catastrophic collision with the Andromeda Galaxy, a neighboring spiral galaxy that currently sits 2.5 million light-years away, but has been inexorably drawn toward us through the patient influence of gravitational attraction, moving ever closer with each passing millennium in a cosmic dance that began long before Earth existed and will conclude long after humanity has vanished from the universe. This collision, often referred to as the Milkomeda Merger or sometimes called the Milkdrome event, represents not an instantaneous catastrophic explosion, as popular imagination might suggest, but rather a slow, grinding process of galactic integration that will unfold across hundreds of millions of years as the two massive spiral structures twist around one another. Their gravitational fields reshaping billions of stars into new configurations, while the supermassive black holes at their respective centers gradually spiral inward toward an eventual merger of their own. The psychological mechanism that allows us to contemplate this scenario with relative calm rather than existential dread seems rooted in temporal distance and abstraction. The time frame involved is so monumentally distant from human experience that our minds cannot truly grasp its proportions, and the event itself operates at scales so vast and processes so slow that they resist visualization in any meaningful way. We have normalized this extraordinary future collision through scientific discourse and educational materials, transforming what would otherwise be an utterly alien and incomprehensible phenomenon into another documented data point in the catalog of cosmic events. Much as we have learned to discuss the eventual death of our sun with detached curiosity rather than overwhelming fear. And in doing so, we have rendered even the most profound transformations of our universe into abstract concepts that we can discuss across dinner tables without experiencing the existential vertigo such contemplation might otherwise provoke. Yet this psychological distance may itself be illusory. The merger's effects will begin long before the galaxies fully integrate, with gravitational disruptions destabilizing planetary orbits and triggering cosmic radiation surges millions of years hence. Reminders that even events separated from us by incomprehensible gulfs of time possess the capacity to reshape the fundamental conditions of existence for whatever conscious beings might witness them. The merger itself will ultimately resolve into a single elliptical galaxy, a fate that awaits nearly all large galaxies in an expanding universe where isolated spiral structures prove ephemeral, suggesting that our current cosmic address, this elegant rotating disk of stars we call home, represents merely a temporary configuration in an unimaginably long sequence of galactic transformations. Deep within the cosmic web that connects all galaxies across billions of light years, there exists a peculiar gravitational phenomenon that astronomers have come to understand with increasing clarity over the past few decades. And this phenomenon is known as the local group isolation effect, which describes the manner in which our local group of galaxies, containing the Milky Way, Andromeda, and roughly 80 smaller satellite galaxies, appears to be moving away from the larger structures of the universe at an accelerating rate that suggests we are becoming progressively more isolated from the cosmic web itself. The real situation involves our local group being pulled and pushed by the gravitational influences of massive structures like the Virgo supercluster and the Great Attractor, yet simultaneously being repelled by vast voids of nearly empty space that surround us on multiple sides, creating what some cosmologists describe as a gravitational island that will eventually become completely severed from the rest of the observable universe. What makes this scenario particularly thought-provoking is the psychological mechanism at work within human consciousness when contemplating such isolation. For there exists a profound and perhaps even primordial fear encoded deep within our collective awareness regarding the concept of separation and abandonment, a fear that extends even to the cosmic scale and manifests itself through our intellectual frameworks as a concern about ultimate isolation in an indifferent universe. The logical underpinning of this fear relates to our evolutionary heritage as social creatures who required group membership for survival, and therefore the notion that our entire galactic neighborhood might be slowly cut off from the rest of existence resonates with something deeply unsettling within our psychology. Yet we continue to normalize this possibility through scientific discussion and theoretical frameworks, treating it as merely another fascinating cosmic mechanism worthy of academic study rather than a source of existential concern, as though by understanding the mathematics behind our cosmic isolation, we somehow render it less threatening or more acceptable as a feature of reality rather than a disturbing trajectory toward ultimate separation and disconnection from everything else that exists. Yet perhaps this intellectual distance we maintain is itself a form of adaptive coping, allowing us to peer into the abyss of cosmic solitude without being paralyzed by it, much as we discuss our own mortality through the frameworks of medicine and biology, transforming raw existential dread into manageable categories of knowledge that we can examine, debate, and ultimately accept as part of the structure of existence itself. In this way, the local group's gravitational separation from the cosmic web becomes not merely a physical phenomenon, but a mirror reflecting how we construct meaning from the incomprehensible forces that shape our place in existence. Imagine the universe as it approaches its final epoch, a time so distant that the word billion loses all meaningful context, a span of years so incomprehensibly vast that even the oldest stars have long since burned away into ash and memory, leaving behind only the faintest echoes of light that will eventually fade into absolute darkness. In this scenario, a single star remains, the last surviving beacon of nuclear fusion in an otherwise dead cosmos, burning alone in an infinite void, surrounded by the cold remnants of stellar death and the inexorable expansion of space itself that grows wider and more isolating with each passing moment. This final star would be orbited by planets or perhaps simply float alone, its radiation pushing against the encroaching darkness in a losing battle against entropy itself, the fundamental law of thermodynamics that ensures all energy gradually disperses into uselessness and cold. The psychological grip of this concept operates on a deeply human level because it embodies our fundamental fear of abandonment and the terror of being the last thing left in existence, the final witness to the universe's own dissolution. We are social creatures wired to exist among others, to find meaning in community and connection, so the image of a solitary star burning in an infinite void strikes at something primal within us, a nightmare of ultimate isolation that we rarely articulate but deeply fear. The concept persists despite our logical understanding that stars do not possess consciousness or fear because we project our own existential anxieties onto the cosmos itself, because we have a habit of anthropomorphizing the universe's indifference into something emotionally resonant. This last star becomes a mirror for our own existential dread, a physical manifestation of abandonment and purposelessness that feels strangely comforting to contemplate precisely because we can observe it from our current position of relative abundance, surrounded as we are by billions of stars and countless forms of life. Perhaps this is why we find ourselves drawn to stories of the last survivor, the final human, the ultimate lonely sentinel, because in contemplating their isolation, we safely rehearse our deepest fears from a distance, transforming cosmic horror into something almost meditative, a philosophical exercise that paradoxically brings us comfort through its very bleakness. And yet, in contemplating this final star's lonely vigil, we might discover an unexpected grace, that even in a universe stripped of nearly everything, the act of burning, of radiating energy outward, of persisting against the void, becomes a kind of meaning in itself, a defiant affirmation that existence need not justify itself through witness or companionship to matter. The last star asks us whether a universe with one burning star is truly empty, or whether solitude and persistence might be forms of beauty we have simply not yet learned to recognize. The Stelliferous Era, which began roughly 13.8 billion years ago with the birth of the first stars, represents the most luminous chapter in cosmic history, a period during which the universe became filled with countless burning furnaces of hydrogen and helium scattered across unfathomable distances. And yet this era, which has persisted through nearly all of observable time as we understand it, will eventually come to an end in a timeframe so distant that it challenges even our most expansive mathematical frameworks to comprehend it fully. Within roughly 100 trillion years, perhaps even stretching toward 1 quadrillion years or beyond, the last stars will exhaust their nuclear fuel, collapsing into white dwarfs, neutron stars, or black holes, and the universe will transition into what cosmologists call the Degenerate Era, a period of unimaginable darkness and cold where the cosmos becomes dominated by the slowly cooling remnants of dead stars and the vast emptiness between them. The psychological weight of contemplating this ending stems from our deep reliance on starlight as a fundamental feature of existence itself. For every atom in our bodies was forged within the cores of ancient stars, and the very concept of a starless universe feels almost paradoxical to our intuition, suggesting a cosmos without light, without warmth, without the visual scaffolding upon which we've built our understanding of space and time throughout human history. We find ourselves mentally unable to genuinely grasp the implications of the Stelliferous Era's conclusion, not because we lack the intellectual capacity to understand the physics involved, but rather because we've internalized stellar abundance as an eternal constant, a background condition against which all other cosmic events are measured. And thus the idea of its absence creates a cognitive dissonance that our minds struggle to resolve with the same ease we might contemplate other forms of cosmic evolution. Despite having detailed astrophysical models that definitively predict this outcome, we rarely dwell on it in our cultural consciousness or in our personal reflections about the future, perhaps because the timescale is so incomprehensibly vast that it seems to possess no practical relevance to human concerns. Yet this very normalization of perpetual starlight, this unexamined assumption that stars will always exist somewhere in the universe in abundance, persists in how we imagine the distant future in our science fiction narratives and in our unconscious expectations about the long-term character of reality itself. Imagine a universe so ancient, so profoundly removed from the present moment, that all the stars have long since burned away into cold cinders, all black holes have evaporated through Hawking radiation, and the only remaining matter consists of isolated protons, neutrons, and electrons spread impossibly thin across an incomprehensibly vast expanse of space. This is the Degenerate Era, a phase of cosmic existence that physicists estimate might begin somewhere between 10 to the power of 40 and 10 to the power of 100 years from now, a timescale so vast that the current age of the universe appears as merely a single heartbeat in comparison. During this epoch, the universe would not be empty in the traditional sense, but rather filled with an incredibly diffuse soup of fundamental particles separated by distances so great that interaction between them becomes virtually impossible, and the temperature of the cosmos would have cooled to mere fractions of a degree above absolute zero. The Degenerate Era persists as a concept in cosmological thinking because it represents a logical extrapolation from our current understanding of particle physics and thermodynamics. If protons do eventually decay, as some grand unified theories suggest, then all nuclei composed of these particles would similarly break apart, leaving behind only leptons and photons in an eternally expanding universe growing colder and emptier with each passing eon. What renders this scenario particularly unsettling to contemplate is that consciousness, life, complexity, and meaning, as we understand them, would become not merely unlikely or improbable, but fundamentally impossible within such conditions. Yet the laws of physics would continue their tireless operation regardless, indifferent to the absence of observers or observers. We persist in discussing this degenerate future despite its apparent meaninglessness and the profound depression it might inspire, largely because the mathematical frameworks that describe our universe naturally lead to such conclusions, making it difficult to simply dismiss or ignore the implications without explicitly rejecting the very theories upon which our modern physics is built. The Degenerate Era remains normalized within scientific discourse precisely because it emerges not from speculation or whimsy, but from the straightforward application of established physical principles extrapolated across timescales so enormous that human intuition becomes entirely useless as a guide to what might actually occur. Picture the universe billions upon billions of years into the future, so distant from our present moment that the very concept of time becomes almost meaningless, where stars have long since burned out and gone dark, where galaxies have fallen into silence, and where the cosmos is populated by nothing but black holes of varying sizes scattered throughout an expanding void of near-perfect emptiness. This is the Black Hole Era, a theoretical epoch that physicists believe may represent the next great chapter in the universe's story, a period that could stretch for durations so incomprehensibly vast that they dwarf the current age of the universe by factors that numbers themselves struggle to represent. According to our current understanding of cosmology and the laws of thermodynamics, once all stars have exhausted their fuel and all stellar remnants have cooled to the temperature of the surrounding space, only black holes will remain as significant structures, gradually consuming whatever little matter drifts into their gravitational reach, slowly transforming the universe into a landscape dominated entirely by these collapsed objects and the vast stretches of darkness between them. The mechanism that drives this era forward is the process of Hawking radiation, a quantum phenomenon where black holes are not actually entirely black, but instead emit a faint radiation due to quantum fluctuations at their event horizons, causing them to lose mass incrementally over incomprehensible timescales, meaning that even these seemingly eternal cosmic monuments will eventually evaporate, taking with them the last vestiges of organized matter in the universe. What makes this theory psychologically compelling is how it presents a vision of cosmic finality that feels both scientifically grounded and deeply unsettling. A slow fade into absolute nothingness that occurs so gradually that it transcends any human frame of reference, transforming the end of everything into a process more subtle than any ending we might normally imagine. We find ourselves drawn to this idea perhaps because it represents a kind of ultimate acceptance, a universe that does not end in dramatic catastrophe, but rather dissipates quietly into entropy, as if exhausted after an eternity of activity, and this gentle apocalypse somehow feels more profound than any violent conclusion, reflecting our deep intuition that all things eventually wind down and fade away. Despite being grounded in legitimate physics, the black hole era remains theoretical and speculative, dependent on assumptions about dark matter, the stability of protons, and quantum gravity that we cannot yet verify. And yet we discuss it with the same confidence we might discuss documented historical events, having normalized this extraordinarily distant scenario as though it were as certain as tomorrow's sunrise. Imagine a universe so old, so vastly expanded, and so thermodynamically exhausted that all the stars have burned out, all the black holes have evaporated through Hawking radiation, and nothing remains but a thin soup of elementary particles drifting through an infinite expanse of absolute darkness and cold, a scenario cosmologists call the Dark Era, which stretches trillions upon trillions of years into a future so distant that our current understanding of deep time becomes almost meaningless. In this theoretical epoch, occurring somewhere between 10 to the 100 to 10 to the 1 Google years from now, the universe would have become so dilute and so devoid of energy that virtually nothing of consequence could happen anymore. And yet this scenario persists in serious scientific discourse, not because it is definitively proven or even particularly likely given our incomplete understanding of cosmology, but because the mathematics that describes the expansion and cooling of our universe, when extrapolated forward through thermodynamic principles and the standard model of particle physics, seems to lead inevitably toward this bleak conclusion. The psychological mechanism that allows us to contemplate such a scenario is rooted in our ability to recognize patterns and project them forward, to follow logical chains of reasoning to their ultimate conclusions, even when those conclusions are profoundly unsettling. And there is something almost meditative about accepting the mathematical inevitability of a universe gradually winding down like a clock losing energy with every tick. A universe that becomes progressively less capable of supporting complexity, consciousness, or meaningful change. What is remarkable is that despite the fact that the Dark Era remains largely theoretical, dependent upon assumptions about dark energy, the stability of protons, and physical constants that we cannot verify over such incomprehensible timescales, we have nonetheless incorporated it into our cosmological narrative as though it were a destination we can reliably predict. Much the way ancient civilizations incorporated mythological end times into their frameworks for understanding existence, demonstrating how thoroughly we have normalized the projection of current physical laws into regimes so extreme that they become almost indistinguishable from metaphysics or mythology themselves. Yet perhaps this exercise in extreme extrapolation serves a deeper purpose than mere predictive ambition. By contemplating the ultimate fate of all structure and energy, we are forced to confront what it means for anything, stars, planets, life, consciousness itself, to be temporary, and in doing so, we inadvertently affirm the preciousness of the present moment in a universe that will not always be capable of wonder. In the final chapters of cosmic existence, long after stars have burned away their fuel and black holes have evaporated through Hawking radiation, the universe enters what physicists call the Photon Age, a period stretching potentially septillion years into the future, where the cosmos becomes nothing more than an infinitely expanding sea of electromagnetic radiation, and the occasional elementary particle drifting through an almost incomprehensibly vast void. During this epoch, the universe has cooled to temperatures so close to absolute zero that no meaningful structures can exist, no atoms can form, no chemical reactions can occur, and consciousness as we understand it becomes a theoretical impossibility in every conceivable corner of existence. The photon age represents a state of such profound emptiness and stasis that it challenges our ability to even imagine what such a reality might entail. Yet it is a genuine prediction arising from our best understanding of thermodynamics and the fate of matter itself. What makes this scenario particularly striking is not its scientific foundation, which is sound, but rather the profound existential vertigo that contemplating it produces within the human mind, a sense that we are examining not merely the distant future, but something closer to the true end of meaning itself. Our brains have evolved to perceive and process information on timescales of seconds to decades, perhaps at most across centuries in our cultural memory. Yet here we are attempting to grasp a future measured in scales that dwarf even the current age of the universe by factors that our language struggles to contain. The photon age persists in scientific literature and popular imagination not because it contradicts our observations, but precisely because it aligns so thoroughly with them, making it seem not like a bizarre speculation, but rather an inevitable conclusion written into the fundamental equations governing reality. We have come to accept this vision of universal decay through a kind of resigned fatalism, acknowledging that if the laws of thermodynamics truly apply universally and eternally, then dissipation and darkness are not threats to be prevented, but rather destinations we cannot escape. There is something almost meditative about contemplating an existence so far removed from our current moment that it transcends anxiety and becomes merely a fact to be considered, like contemplating the geological ages of the Earth without the emotional weight that personal future carries. In accepting the photon age, we accept not defeat but perspective, recognizing that our universe, for all its apparent permanence, is engaged in a very long process of forgetting itself. Imagine the universe as an enormous, perfectly sealed container gradually filling with an invisible fog that cannot be reversed or stopped, a thermodynamic inevitability that physicists call entropy maximum, which describes a theoretical endpoint where all energy has dispersed so completely and uniformly throughout space that no work can ever be performed again, no stars will burn, no chemical reactions will occur. And even the bonds holding atoms together will eventually decay into their fundamental particles, scattered across an infinite void at the same temperature, everywhere simultaneously. This concept emerges from the second law of thermodynamics, one of the most rigorously tested principles in all of science, which states that in any closed system, disorder always increases over time, that heat naturally flows from hot objects to cold objects and never spontaneously reverses, and that the universe itself is constantly moving toward a state of maximum disorder where every gradient that could possibly drive energy or motion has been completely equalized. The mechanism underlying this theory rests on probability and statistics at the most fundamental level, because there are infinitely more ways for energy to be dispersed and disordered than concentrated and ordered, making the dispersed state overwhelmingly more likely to occur spontaneously across the eons. And once every star has exhausted its fuel, every black hole has evaporated through Hawking radiation, and every atom has decayed through processes we barely understand. The universe will exist in a state of perfect thermal equilibrium with no temperature differences anywhere. What renders this scenario so peculiar and haunting despite its rigorous mathematical foundation is that we have normalized the idea that our existence depends entirely on the temporary cosmic deviation from entropy maximum, that all of life and consciousness and meaning emerges only in this brief, flickering window of disequilibrium where energy gradients still exist, and that we are essentially riding a wave of order that must eventually crash into infinite disorder. Yet we carry on our daily lives with barely a conscious acknowledgement that the heat death of the universe is not merely possible, but thermodynamically inevitable given enough time, suggesting that we compartmentalize this knowledge in ways that protect our psychological functioning while simultaneously knowing its truth. Perhaps this is why we build monuments and write books and compose symphonies, why we create anything at all, because somewhere beneath our rational understanding of thermodynamic inevitability lives an ancient, stubborn impulse to impose order, to arrange matter into meaning before it all dissolves back into undifferentiated noise, a defiant act of temporary organization against the universe's patient drift toward silence. Consider the ultimate fate of a universe that continues expanding forever, one in which the acceleration caused by dark energy never reverses, and all the matter and energy within it gradually spreads so thin that the cosmos becomes an almost incomprehensibly vast void, where particles drift through absolute darkness at distances so great that light itself takes an eternity to travel between them. This scenario, often called the Big Freeze or Heat Death, represents a universe in which entropy reaches its theoretical maximum state, where all stars have burned out, all black holes have evaporated through Hawking radiation over unimaginable timescales measured in zillions of years, and even the elementary particles themselves begin to decay and vanish from existence, leaving behind only diffuse radiation spread so uniformly across the expanding void that no structure, no complexity, and no consciousness could ever emerge again. The psychological weight of contemplating this particular end state lies in its profound indifference to all meaning we might assign to existence. For unlike other extinction scenarios that involve violent cataclysm or dramatic collapse, the Big Freeze describes a slow, inexorable cooling where the universe simply winds down like an aging mechanism, eventually reaching a state of perfect equilibrium where nothing happens, nothing changes, and nothing can ever happen again for all eternity. We have normalized this concept despite its overwhelming existential implications by treating it as a scientific likelihood rather than confronting its philosophical dimensions, allowing ourselves to discuss it in academic terms and probabilistic language as though discussing a distant, whether pattern rather than the ultimate negation of existence itself. The theory persists not because we have emotionally integrated it, but because our minds seem peculiarly capable of compartmentalizing such truths into intellectual frameworks where they become manageable abstractions, allowing us to contemplate our own mortality and that of all things without triggering the full weight of despair that such contemplation logically should produce. Yet perhaps this very capacity for compartmentalization serves a crucial function. It permits us to continue building, creating, and loving in the present moment despite knowing that all our works will eventually dissolve into the cosmic background radiation, suggesting that meaning might not require permanence, and that consciousness itself may be valuable precisely because it burns so briefly against the gathering dark. Consider the possibility that the universe does not end in a spectacular catastrophe, but rather in a gradual, almost imperceptible fade into nothingness, a slow dissolution so subtle that observers within it might not even notice the transition from existence to void until the very last moment arrives. This theory proposes that instead of a dramatic big rip that tears apart the fabric of spacetime, or a crushing big crunch that collapses all matter into a singular point, the cosmos simply diminishes in energy and vitality over incomprehensible stretches of time, losing its capacity to sustain even the most basic physical processes. Imagine protons themselves eventually decaying into lighter particles, stars burning out and leaving only cold cinders drifting through an expanding darkness, and black holes evaporating through Hawking radiation until nothing remains but a diffuse soup of radiation so spread out and so cold that it contains virtually no usable energy whatsoever. The psychological mechanism behind this theory relates to our deep discomfort with genuinely slow processes, our inability to emotionally grasp timescales that extend beyond millions or billions of years, making the concept feel almost more unsettling than violent endings because our minds struggle to fully imagine a transition so gradual that it lacks dramatic narrative structure. We have normalized catastrophic thinking about extinction events, incorporating them into our cultural stories and scientific frameworks, yet the Big Whimper persists as a counterintuitive alternative despite its far greater likelihood according to current cosmological models, suggesting that even when presented with the most probable scenario, we somehow prefer our apocalypses with volume and intensity rather than silence and imperceptible decay. Perhaps this preference reveals something fundamental about human consciousness itself, that we are creatures shaped by narrative arcs and climactic moments, making it nearly impossible for us to achieve genuine emotional resonance with a story that simply trails off into ellipsis rather than concluding with punctuation, and thus we unconsciously resist the cosmological model that most accurately reflects our actual destiny. We construct monuments and write epic poems about civilizations that fall dramatically, Pompeii buried in ash, Rome sacked by invaders. Yet we have no cultural vocabulary for decline so gradual that each generation barely notices the world is slightly dimmer, slightly colder, slightly more exhausted than the one before, until eventually there is nothing left to notice at all. In this way, the Big Whimper may be the most terrifying cosmological fate precisely because it demands we confront not a moment of ending, but an infinite series of ordinary moments that, taken together, amount to everything ceasing to be. Imagine the universe not ending with a bang or a whimper, but instead collapsing inward upon itself in what some theoretical physicists have termed the Big Splat, a catastrophic scenario wherein the fundamental fabric of spacetime doesn't gradually decay or expand forever into cold darkness, but rather implodes with such violent intensity that all matter, energy, and information within the cosmos compress into an infinitely dense singularity, only to immediately and explosively scatter outward in a chaotic spray of particles, radiation, and twisted dimensional fragments that expand in all directions simultaneously without any coherent structure or pattern whatsoever. The mechanism underlying this theory rests on a particular interpretation of quantum mechanics and general relativity working in tandem, suggesting that the universe exists in a state of precarious equilibrium, balanced upon the knife's edge between expansion and contraction, and that under the right conditions, or perhaps under entirely random fluctuations that occur across cosmic timescales, this equilibrium could catastrophically fail, causing spacetime itself to undergo a phase transition similar to water suddenly freezing or boiling, but on an infinitely larger scale. In this scenario, the laws of physics as we understand them would cease to function meaningfully, causality would unravel, and the very concept of before and after would lose all coherence, making the Big Splat not just the end of everything, but the end of the framework through which we even conceptualize endings themselves. What persists about this theory despite its speculative nature and its existence at the very margins of conventional cosmology is humanity's deep psychological need to imagine the universe's fate in visceral, almost violent terms, as though the cosmos must end not with serenity but with drama and chaos, reflecting perhaps our own anxieties about loss of control and the fundamental unpredictability of existence. And we continue to theorize about such scenarios precisely because they resonate with something primal in human consciousness, something that finds strange comfort in imagining catastrophe rather than accepting the possibility of endless, meaningless stasis. Perhaps this is why the Big Splat, despite its negligible probability and questionable theoretical grounding, has captured the imagination of cosmologists and science fiction writers alike. It offers a narrative conclusion rather than mere entropy, a story of cosmic drama that mirrors the apocalyptic myths found across human cultures, from Ragnarök to the Book of Revelation, suggesting that our attempts to formalize the universe's death may ultimately reveal more about how we narrate meaning than about how the cosmos actually ends. In this sense, the Big Splat functions as a kind of existential mirror, allowing us to project our fears of annihilation onto the cosmic stage and thereby transform personal dread into something grander and more intellectually manageable. Imagine the universe as we know it slowly collapsing into a single point, not through the violent crushing of a big crunch or the gradual cooling of heat death, but rather through a process so quiet and mundane that it might as well be sipping the cosmos through an invisible straw. This is the Big Slurp, a theoretical endpoint proposed by some physicists in which a bubble of true vacuum, born from quantum fluctuations in the false vacuum that currently surrounds us, begins to expand at the speed of light, consuming all of reality as it spreads outward from some distant corner of the universe. The mechanism is rooted in quantum field theory and the peculiar mathematics of vacuum states, suggesting that our current universe exists in an unstable, excited state rather than at its lowest possible energy level, much like a ball balanced precariously at the top of a hill rather than nestled safely at the bottom. If a fluctuation were to occur somewhere in the cosmos, a region of lower energy would suddenly expand, rewriting the fundamental laws of physics as it advances, fundamentally transforming matter and energy into configurations we cannot even imagine, structures so alien to our existence that atoms themselves would cease to have meaning. The expansion would be absolutely unstoppable because nothing, not even light itself, travels faster than the advancing boundary of this new reality, making it a perfect and inevitable doom with no warning and no escape for any civilization unlucky enough to exist within its path. What makes the Big Slurp persist as a concept in scientific discourse, despite its remote probability, is precisely the fact that it exposes a genuine uncertainty in our understanding of the vacuum itself, reminding us that even the emptiest space might harbor hidden instabilities, and that the very ground beneath existence might be far less stable than our everyday experience suggests. Lending an almost meditative quality to contemplating a universe that could be unmade at any moment by the simple switching of a cosmic light switch, happening somewhere we will never see and at a time we will never know. Yet despite this sobering physics, the Big Slurp remains extraordinarily unlikely in our universe's timeline. Current observations suggest our vacuum is remarkably stable, and the probability of such a catastrophic phase transition occurring anytime soon borders on the infinitesimal, offering us the peculiar comfort that we are almost certainly safe from this particular cosmic doom, at least for the foreseeable future. Still, the intellectual exercise of contemplating the Big Slurp serves a deeper purpose. It humbles us by revealing that our universe's continued existence is not guaranteed by any law of nature, but rather depends on the particular configuration of quantum fields we happen to inhabit, a reminder that our cosmic address might be less permanent than the stars themselves suggest. Imagine the final moments of our universe as we understand it, when entropy has reached its absolute maximum and all matter has decayed into its most fundamental constituents, scattered across an infinite expanse of near-absolute zero darkness. In this scenario, quantum mechanics presents us with a peculiar and counterintuitive possibility that exists at the boundary between genuine physics and speculative philosophy, one that suggests the universe itself might tunnel through the probabilistic barriers of existence and spontaneously reappear in a new configuration, much like a particle that appears on the opposite side of a wall without ever passing through it. The real-life foundation for this concept rests upon the well-established quantum mechanical principle of tunneling, where particles demonstrate the ability to traverse energy barriers that should theoretically be impenetrable according to classical physics, a phenomenon that has been observed countless times in laboratories and forms the basis of technologies like tunnel diodes and scanning tunneling microscopes. Applied to cosmological scales, this mechanism suggests that even when the universe reaches its ultimate heat death, the quantum vacuum itself contains the potential for extraordinary fluctuations, and given an infinite timeline, the probability of a spontaneous quantum event triggering a new Big Bang or creating a pocket universe becomes mathematically non-zero, however infinitesimal that probability might be. The psychological appeal of this theory stems from humanity's deep-rooted discomfort with absolute finality and our ancient mythological patterns of cyclical renewal, death and rebirth narratives that have comforted us across cultures and millennia, allowing us to project these archetypal stories onto the cosmos itself and imagine that even ultimate destruction carries within it the seed of renewal. We find comfort in the notion that nothingness might be temporary, that the void could birth itself anew, and that even the heat death of the universe represents not a true ending but merely a pause, a hibernation before quantum probability rolls its dice once more and consciousness or existence in some form emerges again from the quantum foam. What makes this theory particularly persistent despite its extreme speculative nature is that it exists in the shadows between what we can prove and what mathematics technically permits, occupying a space where rigorous physics becomes indistinguishable from metaphysical hope. And we have largely accepted this ambiguity as a permanent feature of modern cosmology rather than recognizing it as a profound uncertainty we must eventually resolve. Yet perhaps this unresolved ambiguity itself serves a purpose, for in clinging to the mathematical possibility of rebirth, we acknowledge both our scientific humility and our refusal to accept that meaning must end simply because matter does. In the deepest mathematical models of quantum mechanics and cosmology, there exists a peculiar notion that the universe might not truly end in any permanent sense, but rather experience something akin to a cosmic fluctuation that could theoretically reset everything back to its initial conditions, allowing an entirely new universe to emerge from the quantum vacuum in a process sometimes called the Fluctuation Reboot. According to this theory, if we wait long enough, far longer than the current age of the universe multiplied by itself countless times, random quantum fluctuations operating at the most fundamental scales of reality might spontaneously generate a pocket of spacetime with different or identical initial conditions to our own, essentially creating a new Big Bang from nothing. And this process could theoretically happen not just once, but infinitely many times across infinite timescales, suggesting that universes might spawn from universes in an endless recursive cycle of creation and dissolution. The mechanism behind this concept rests on the understanding that quantum field theory permits virtual particles to briefly emerge from the vacuum, and if the conditions align correctly through an incomprehensibly unlikely sequence of fluctuations, an entire inflationary bubble could nucleate, with all the energy and structure necessary to birth a complete cosmos fully formed and ready to evolve through its own epochs. The psychological appeal of this theory lies in its offer of a strange comfort, the notion that nothing is ever truly lost or final, that destruction and creation are eternally linked in an infinite dance, and that even the heat-death of our universe might be merely one chapter in an endless story of cosmic recycling. We find ourselves drawn to this idea despite its unfathomable timescales and the utter insignificance it assigns to our universe, perhaps because it echoes ancient mythological and religious concepts of cyclical time and eternal renewal, transforming scientific nihilism into something that feels almost like hope in the darkness. Yet in contemplating such infinite recursion, we might ask whether our own universe itself is merely one reboot in an unimaginable sequence, whether the initial conditions we observe, the fundamental constants, the arrow of time, the very laws of physics, might be echoes or variations of countless predecessors, and whether this possibility fundamentally alters how we should understand our place in a cosmos that may be far stranger and more fecund than our current science can articulate. Imagine that our universe exists as a vast holographic projection, a three-dimensional reality encoded on a two-dimensional boundary at the edge of existence, much like how a hologram contains all the information of a three-dimensional image within a flat surface. And imagine further that this boundary begins to fail, to crack and deteriorate like an old film reel breaking apart in a projector, causing the information that sustains our reality to become corrupted and distorted, until eventually the entire three-dimensional world we inhabit simply ceases to cohere, unable to maintain its existence without the functioning boundary that creates it. This concept emerges from string theory and quantum physics, where researchers have proposed that our universe might be fundamentally two-dimensional at its deepest level, with what we perceive as three-dimensional space being an elaborate illusion created by information encoded on a distant surface. And if this encoding system were to deteriorate, perhaps due to cosmic radiation, the accumulation of quantum errors over billions of years, or some form of fundamental decay built into the nature of information itself, then reality would begin to unravel at the smallest scales before expanding outward into macroscopic collapse. The psychological mechanism that makes this theory so compelling despite its abstract nature is our deep uncertainty about what reality fundamentally is, our sense that the solidity beneath our feet might be theater, that consciousness itself observes a performance rather than accessing genuine substance. And this uncertainty taps into ancient philosophical anxieties about illusion and authenticity that have persisted across human cultures for thousands of years. What makes the holographic boundary failure particularly unsettling is how it reframes not just our universe's ending, but the very meaning of existence itself, suggesting that the end would not be dramatic or catastrophic in the traditional sense, but rather a gradual failure of the mechanism that makes anything real, a slow dimming of the projection, and yet we continue to live and build and plan as though the boundaries of reality were infinitely stable and reliable. Accepting without question this fundamental uncertainty about whether the ground beneath us is truly there or merely an elaborate encoding that could fail at any moment without warning or explanation. Perhaps this is why we instinctively seek meaning in patterns and structures, why we build monuments and write books and preserve knowledge, acts of defiance against the possibility that our efforts to encode information might be no different from the cosmic process that sustains us, equally fragile and temporary, equally subject to the slow entropy that consumes all systems, whether they exist on the boundary or within the projection itself. Deep within the mathematical framework of black hole physics lies a concept so troubling that it has fractured the confidence of theoretical physicists for nearly 2 decades, a puzzle known as the Firewall Paradox, which emerges from a fundamental collision between quantum mechanics and general relativity at the event horizon itself. According to classical general relativity, an observer falling into a black hole should experience nothing particularly unusual at the event horizon, crossing the point of no return without any dramatic or violent occurrence, a concept formalized in what physicists call the equivalence principle, which suggests that the local physics experienced by a freely falling observer should be indistinguishable from the physics in flat spacetime. However, when quantum mechanics enters the picture through the concept of Hawking radiation, a profound contradiction emerges, because Stephen Hawking demonstrated that black holes are not truly black, but instead emit radiation due to quantum fluctuations near their event horizons, and this radiation carries away information about the black hole's interior. This creates an information paradox, for if the black hole eventually evaporates completely, the quantum information that fell into it appears to be lost forever, violating a fundamental principle of quantum mechanics that information cannot be destroyed. In 2013, Juan Maldacena and colleagues proposed that to preserve quantum mechanics and resolve the information paradox, the event horizon itself must transform into what they called a firewall, a region of extraordinarily high-energy radiation that would incinerate any infalling observer before they could cross the boundary, a violent and turbulent surface rather than the smooth, innocuous horizon predicted by general relativity alone. The psychological mechanism underlying the firewall paradox's persistence in cosmological discourse stems from its representation of an unsolvable dilemma at the heart of our deepest theories. For we possess two frameworks of extraordinary success and precision, yet when applied to black holes, they produce mutually exclusive predictions, leaving physicists suspended between accepting information loss or accepting a violent firewall that seems to violate the equivalence principle. This paradox has persisted despite decades of intense scrutiny because no resolution has achieved universal acceptance within the physics community, and proposed solutions such as fuzzballs, wormholes connected to other universes, or modified quantum mechanics each carry their own conceptual costs and lack decisive observational evidence. Yet the firewall paradox endures in our conversations about cosmic endings precisely because it represents something we have normalized in modern physics, the acceptance that the universe operates according to principles that may be fundamentally incompatible at extreme scales. When a black hole consumes matter and energy, it appears to violate one of the most sacred principles in physics, the conservation of information, which states that information about the state of a system can never truly be destroyed, only transformed or hidden. Stephen Hawking's discovery that black holes emit radiation and eventually evaporate created what became known as the information paradox, a profound puzzle suggesting that all the information about everything that fell into a black hole would be lost forever when the black hole disappeared, leaving the universe with less knowledge about its own history than it should possess. This theoretical scenario haunts physicists because it suggests either that quantum mechanics is fundamentally wrong, or that black holes contain some hidden mechanism for preserving information that we simply do not yet understand, or perhaps most troublingly, that information genuinely vanishes from the universe in a way that contradicts our deepest assumptions about how reality operates. The paradox persists even though decades of brilliant theoretical work have attempted to resolve it through concepts like holographic principles, firewalls at event horizons, and quantum hair that encodes information on the black hole's exterior. Yet despite these proposed solutions, no consensus emerges, and physicists continue to debate whether the universe truly has perfect memory, or whether the very concept of information preservation is merely a comforting fiction we have imposed upon physical law. What makes this paradox particularly disorienting is how it forces us to confront the possibility that the universe might be fundamentally lossy, that the arrow of time might not simply point forward but might also erase, and that the future state of all existence could depend on information that is permanently inaccessible, creating a cosmos that forgets its own origin and proceeds through time guided only by probabilities and shadows of what came before. If information truly vanishes into black holes, then the universe would be fundamentally indeterminate. Each moment would birth new possibilities unconstrained by complete knowledge of the past, making reality less a clockwork of predetermined consequences and more a perpetual act of creation where the future genuinely remains open, untethered from the chains of perfect causality that Newton and Laplace once imagined governed all things. Yet this realization, that information might be genuinely lost, also suggests a strange liberation. If the universe need not remember everything perfectly, then consciousness itself, with all its selective forgetting and reconstructed memories, might be less an anomaly in a deterministic cosmos and more a natural expression of how reality fundamentally operates, where meaning emerges not from perfect preservation, but from the act of observation and interpretation itself. In the landscape of theoretical physics, there exists a peculiar mathematical space known as anti-de Sitter space, abbreviated ADS, which describes a universe with negative curvature and a very particular relationship to gravity and quantum mechanics. This geometric framework, discovered within Einstein's field equations, has become increasingly central to modern theoretical physics, particularly through the groundbreaking ADS/CFT correspondence discovered by Juan Maldacena in 1997. The anti-de Sitter transition scenario proposes that our universe, which currently appears to exist within a de Sitter space characterized by positive curvature and accelerating expansion driven by dark energy, might undergo a fundamental phase transition into an anti-de Sitter configuration. This transition would represent not merely a change in cosmic conditions, but rather a restructuring of the very mathematical foundation upon which reality operates, fundamentally altering the nature of spacetime geometry itself. The mechanism underlying this theoretical possibility emerges from the recognition that our universe's positive cosmological constant, the mysterious dark energy driving accelerated expansion, might not be permanent or stable. If quantum fluctuations or some unknown interaction were to reverse the sign of this cosmological constant, transforming it from positive to negative, the entire structure of spacetime would undergo a catastrophic reconfiguration. The universe would cease to expand and would instead begin to contract along an exponentially accelerating trajectory, with all matter, energy, and information being drawn toward a geometrically defined boundary at infinity. What remains psychologically compelling about this scenario, despite its abstract mathematical nature, is how it resonates with deep human intuitions about transformation and inevitability. The notion that the fundamental rules governing existence might shift so completely that the very geometry in which all physical processes occur could transform into something unrecognizable touches upon our instinctive understanding of apocalypse and fundamental rupture. We have become so accustomed to thinking of physical laws as eternal and unchanging that the possibility of their restructuring at the deepest level seems almost incomprehensible. Yet we have normalized this impossibility through decades of theoretical work and mathematical formalism, discussing it in the language of equations and phase transitions, until it becomes intellectually digestible despite remaining fundamentally alien to our experiential understanding. Imagine that in the deep future, when the universe has expanded to an almost incomprehensible degree, and all the luminous matter has long since decayed into radiation and exotic particles, there emerges a phenomenon so subtle yet so profound that it fundamentally alters the fabric of reality itself, a process whereby the countless neutrinos that pervade every corner of existence begin to behave in ways that defy our current understanding of quantum mechanics and particle physics. These ghostly particles, which pass through ordinary matter by the trillions every second without leaving a trace, have always been understood as isolated and independent entities that rarely interact with anything around them. Yet in this theoretical scenario, they gradually accumulate and condense into a new form of matter under the weight of the universe's own expansion and the weakening of fundamental forces. The mechanism underlying this bizarre transformation rests on the assumption that, as the cosmos continues to cool and expand, the conditions that normally keep neutrinos in their dispersed state would eventually reverse, allowing them to cluster together through processes we barely understand today, forming a kind of neutrino superfluid or condensate that permeates all of space and acts as a new substrate for reality itself. This condensation would happen so gradually across incomprehensible timescales that conscious observers, should any exist to witness it, would experience only the gentlest of transformations, perhaps noticing that light behaves differently or that the very constants of nature begin to shift imperceptibly, creating a slow fade into a universe governed by entirely different rules. What makes this theory persist in the minds of theoretical physicists and cosmologists, despite lacking significant observational evidence or even a complete mathematical framework, is that it addresses a real problem in fundamental physics, namely what happens to neutrinos in the far future and how the universe's ultimate fate might be determined by the behavior of its most abundant particles. Granting it a veneer of legitimacy that keeps it alive in academic conversations and speculative papers, allowing us to continue entertaining the possibility that the universe's ending might not be a dramatic event, but rather a quiet transformation into something we cannot yet name or comprehend. In such a universe transformed by neutrino condensation, the very distinction between particle and field would blur into meaninglessness, and what we now call the vacuum of space might reveal itself to have been merely an embryonic state, waiting through eons for the conditions necessary to birth a cosmos of unimaginable complexity from the patient accumulation of nature's most elusive messengers. Imagine the universe as a vast ocean of energy that persists even in the complete absence of matter, a phenomenon physicists call vacuum energy or the cosmological constant, and imagine further that this fundamental energy that fills every cubic centimeter of empty space is not stable or fixed, but rather slowly drifting over the course of billions of years, gradually increasing or decreasing in ways that we cannot predict or fully comprehend. This theory of vacuum energy drift suggests that the seemingly constant value of empty space itself might be undergoing a subtle but inexorable transformation across cosmic timescales, meaning that the very fabric of existence is not a reliable anchor point, but rather a slowly shifting foundation beneath reality, like standing on ice that is imperceptibly melting away. The mechanism that sustains this concept in scientific thought, despite its deeply troubling implications, lies in the observation that quantum field theory permits fluctuations and uncertainty at all scales, including at the level of the vacuum itself. And if we extrapolate these quantum uncertainties across the unimaginable timescales of the universe's existence, it becomes theoretically possible that the energy density of empty space could experience a slow drift. A gradual settling or shifting that would take longer than the current age of the universe to complete, yet would still represent a genuine change in the most fundamental constant of existence. What makes this theory particularly difficult to refute is that such a drift would occur on timescales so vast that it would be effectively unobservable to any civilization, including our own, creating a situation where the universe could be undergoing profound transformation while remaining perpetually imperceptible to all observers. And this combination of scientific plausibility with absolute unobservability makes the theory simultaneously compelling and utterly untestable. The psychological persistence of vacuum energy drift as a concept worthy of serious consideration reflects our deepening unease with the idea that the universe operates according to truly permanent, unchanging laws. Because if even the vacuum itself can drift, then nothing in existence possesses genuine stability. And this existential vertigo has become normalized within theoretical physics as simply another possibility to be catalogued and contemplated alongside the other scenarios for cosmic evolution and eventual demise. The contemplation of such imperceptible cosmic drift also forces us to reconsider what we mean by laws of nature, whether they are truly immutable principles written into the fabric of reality, or whether they are merely regularities observed during a particular epoch of cosmic history, subject to drift and transformation on scales that render the distinction between permanence and change philosophically meaningless. Imagine the fabric of space and time itself containing infinitesimal threads of pure energy, relics from the universe's first fraction of a second, woven throughout the cosmos like invisible scars left behind by the Big Bang's violent expansion. And picture these cosmic strings as one-dimensional defects, so extraordinarily thin yet so densely massive that a single thread extending across the entire observable universe would weigh less than a mountain. Yet possess the gravitational force to bend light and warp spacetime in ways that challenge our fundamental understanding of physics and reality itself. These cosmic strings exist not in the realm of pure speculation, but emerge from legitimate particle physics and string theory mathematics, predicted as inevitable byproducts of symmetry breaking in the early universe, consequences as natural as ripples forming on water when you disturb its surface. Yet unlike ordinary matter and energy that dissipate and decay, these strings could persist for billions of years, moving through the cosmos at nearly the speed of light, occasionally crossing themselves in what physicists call intercommutation events. The collapse theory proposes that as the universe expands and cools, these cosmic strings gradually lose energy and begin to form loops that oscillate and radiate away their gravitational potential, eventually evaporating entirely. But here lies the profound mechanism of this scenario. The collapse would not occur uniformly across all cosmic strings simultaneously, instead creating regions where strings persist longer than others, forming a kind of cosmic skeletal framework that gradually dissolves. And depending on the density and distribution of these strings, Their collapse could trigger cascades of gravitational waves, topological defects unraveling across light years of space, potentially destabilizing the expansion rate of the universe itself, or causing localized spacetime ruptures that propagate outward in patterns we cannot yet predict. What makes cosmic string collapse particularly unsettling as a mechanism for universal ending is that despite decades of searching with the most sensitive gravitational wave detectors and observational instruments humanity possesses, we have found no definitive evidence that cosmic strings actually exist in our universe at all. Yet the theory persists in scientific literature, refined and elaborated, treated as a plausible scenario worthy of serious consideration. Normalized through its inclusion in cosmological models and theoretical frameworks, almost as though the absence of evidence has become irrelevant compared to the mathematical elegance of the hypothesis itself, allowing physicists to continue building elaborate narratives about universe-ending scenarios predicated on phenomena that may be entirely fictional, demonstrating how theoretical possibility can acquire the weight and persistence of near certainty through the sheer intellectual investment we place in exploring it. Imagine the universe not as a smooth, continuous fabric, but as a crystalline structure riddled with microscopic imperfections, much like a real crystal contains tiny fractures and dislocations that weaken its overall integrity. Topological defects are precisely these kinds of flaws, theoretical wrinkles in spacetime itself that formed during the earliest moments after the Big Bang when the universe underwent rapid phase transitions, similar to how water suddenly freezes into ice and creates stress fractures in the process. These defects come in several varieties. Cosmic strings are one-dimensional cracks stretching across the cosmos, domain walls are two-dimensional sheets that divide regions of different physical properties, and monopoles are point-like singularities in the fabric of reality itself. The Cascade scenario proposes something far more troubling than their mere existence, suggesting instead that these defects do not remain isolated, but rather interact with one another in a chain reaction of increasing severity and density. As the universe ages and continues to expand, these defects would gradually accumulate and collide with greater frequency, and with each collision, they might generate new defects or amplify existing ones, creating a cascading instability that spreads outward like cracks spiderwebbing across a windshield after initial impact. The psychological appeal of this theory lies in its resonance with our experience of cascade failures in systems we understand, from avalanches to market crashes to system-wide blackouts, where small initial conditions trigger exponentially larger consequences that seem to defy proportion or reason. We find ourselves drawn to this explanation because it mirrors the anxiety we feel about complex systems reaching critical thresholds beyond which recovery becomes impossible. The theory persists in academic circles despite having virtually no observational evidence supporting it, because it elegantly combines fundamental physics principles with deep-seated human fears about hidden structural weaknesses waiting to unravel everything we depend upon, and because the very nature of topological defects means they might remain forever beyond our ability to directly detect them, until the moment their cascade becomes catastrophic and irreversible. In this sense, the topological defect cascade represents a uniquely modern anxiety. The dread of invisible infrastructure failures that we cannot inspect or reinforce, defects woven into reality's foundation before we evolve to comprehend them, leaving us forever unable to distinguish between a universe that is genuinely fragile and one that merely appears so through the lens of our incomplete understanding. Imagine a cosmos so cold that all motion ceases entirely, where atoms themselves fall into absolute stillness, and every particle in existence becomes locked in an eternal freeze, suspended in a crystalline void of zero kinetic energy. This is the concept of the universe freezing solid, a scenario that emerges from our understanding of thermodynamics and the universe's ultimate fate, where temperature approaches absolute zero and all heat dissipates into the infinite expanse until nothing warm remains anywhere. The mechanism driving this theory stems from the second law of thermodynamics, which dictates that entropy in a closed system always increases over time, meaning that all usable energy gradually converts into unusable heat, and this heat itself disperses outward into space without concentrating anywhere, causing the overall temperature of the universe to decline infinitely. As the universe expands and cools across trillions upon trillions of years, stars burn out and fade to ash, black holes evaporate through Hawking radiation, and eventually even the fundamental particles themselves may decay into lower energy states, leaving behind a universe so devoid of thermal energy that frozen stillness becomes the defining characteristic of existence. The psychological grip of this scenario rests on our intuitive understanding that cold represents death, stagnation, and the absence of the activity that makes existence feel alive and dynamic. We have normalized the concept of heat as synonymous with life and motion, while cold connotes emptiness and void, so the image of absolute freezing strikes at something primal within our consciousness about finality and cessation. Yet despite the grim implications, this theory persists in scientific discourse and popular imagination precisely because it follows logically from established physics rather than requiring speculation beyond known laws, making it feel more inevitable and real than more fantastical scenarios. The frozen universe remains with us as a thought experiment because it represents not a violation of natural law, but rather the inevitable conclusion of laws we have already measured and verified, offering a strange comfort in its absolute predictability. In this ultimate entropy, even the concept of time itself becomes meaningless. Without energy gradients or changes occurring anywhere, there would be no clock to measure duration, no process to mark before from after, leaving only an infinite stillness that is simultaneously the end of everything, and a state so static it transcends the very notion of existence itself. Perhaps this is why the heat death of the universe haunts us more deeply than any violent apocalypse, not because it arrives with catastrophic fury, but because it whispers of a slow, inexorable fade into silence, where even the memory of warmth and change dissolves into the indifferent mathematics of thermodynamic equilibrium. Imagine a structure so fundamentally alien to our experience of reality that it exists in a state of perpetual motion without ever truly moving forward, a physical manifestation of a paradox so profound that physicists initially dismissed it as mathematically impossible. Yet recent experimental evidence suggests that time crystals might represent one of the universe's most elegant solutions to the problem of eternal stasis. Time crystals are theoretical objects that break time symmetry in the same way ordinary crystals break spatial symmetry, meaning they possess an internal structure that repeats in time rather than space, oscillating in a repeating pattern that requires no external energy input to maintain, existing in what researchers call a ground state of eternal recurrence. In our current understanding of physics, this should be impossible because the laws of thermodynamics seem to forbid perpetual motion and eternal cycles. Yet the mathematics describing certain quantum systems point toward configurations where this becomes not merely possible but inevitable, suggesting that at the universe's end, when all other forms of matter and energy have decayed beyond recognition, time crystals might persist as the final monuments to existence itself. The mechanism underlying this strange possibility rests on quantum mechanical principles that allow certain systems to exist in superposition, where particles occupy multiple states simultaneously, creating interference patterns that reinforce themselves eternally without degradation or loss, a bootstrapping effect where the system's own quantum nature prevents it from settling into thermodynamic equilibrium. What makes time crystals particularly relevant to theories of universal endings is their potential to exist indefinitely, representing a form of immortality written into the fabric of quantum mechanics itself. Yet we have normalized this concept despite its deeply counterintuitive nature, treating it as merely another mathematical curiosity rather than acknowledging that if time crystals can truly persist forever, they might be the universe's last breath. The final echo of existence long after stars have cooled and galaxies have dispersed into an infinite void of darkness and cold silence. Perhaps this is why some theoretical physicists have begun to wonder whether time crystals represent not an ending, but a doorway, a mechanism by which information and order might survive the heat death of the universe, suggesting that eternity itself might not be the absence of all things, but rather an infinite, crystalline dance of quantum patterns repeating endlessly in the darkness. Imagine a universe where the act of observation itself becomes the mechanism of its own preservation, where reality freezes in place not because time has stopped, but because consciousness itself has become the watchful guardian preventing any change from occurring at all. This is the essence of the quantum xeno-universe theory, a deeply unsettling extrapolation of quantum mechanics that suggests the cosmos might be locked in an eternal state of stasis, unable to evolve or decay or transform into anything other than what it currently is. The theory draws its name from Zeno of Elea, the ancient Greek philosopher who proposed paradoxes about motion and change, but it derives its quantum mechanical foundation from what physicists call the quantum Zeno effect, a phenomenon in which a quantum system that is repeatedly measured or observed will remain in its initial state and be prevented from evolving or decaying into other possible states. According to this peculiar cosmological hypothesis, if the universe itself is somehow being continuously observed or measured by some fundamental aspect of existence, whether through quantum interactions at the Planck scale or through some form of universal consciousness or information processing, then the constant measurement would prevent the universe from undergoing any fundamental transformations or transitions that might otherwise occur through natural decay processes or quantum tunneling events. The psychological mechanism behind this theory involves our deep-seated fear of stagnation combined with the simultaneous comfort we derive from permanence and stability. We construct elaborate narratives in which nothing truly changes because everything is locked in observation, creating a paradox where the very mechanisms that would normally allow for growth and transformation become the instruments of eternal sameness. There is something almost meditative about this idea, a strange reassurance hidden beneath the surface of cosmic paralysis. For if the universe cannot change, then neither can we, and in that immobility lies a kind of peace that transcends the anxiety typically associated with cosmic endings or transformations. The theory persists in cosmological discussions not because evidence supports it, but because it offers a unique intellectual framework through which to contemplate the relationship between consciousness and reality, between observation and existence, between the act of measurement and the nature of time itself. Within this framework, we might ask whether the universe's apparent arrow of time, its relentless progression from past to future, is itself merely the illusion created by our inability to observe everything simultaneously, suggesting that true stasis may have always been the cosmos's default state, with change being nothing more than the subjective experience of incomplete observation. In quantum mechanics, there exists a peculiar phenomenon known as wave function collapse, wherein the act of observation or measurement appears to fundamentally alter the state of a quantum system, causing it to transition from a state of superposition into a definite measurable reality. According to this interpretation, before an observer measures a particle, it exists in multiple states simultaneously, described by a mathematical wave function that encompasses all possible outcomes. The moment a conscious observer or measuring device interacts with this system, however, the wave function instantaneously collapses into a single, definite state, and only then does the particle acquire the properties we can actually observe and measure. This strange phenomenon has led some theoretical physicists and cosmologists to speculate on a far grander scale about the nature of the universe itself and its ultimate fate. If observation truly collapses quantum states and brings reality into being through the act of measurement, then perhaps the universe itself exists in a kind of superposition, a vast collection of potential outcomes and configurations, and the presence of conscious observers throughout the cosmos serves as a fundamental requirement for maintaining the universe's coherent, collapsed state. Under this interpretation, consciousness and observation are not merely passive reflections of reality, but are instead active participants in the universe's continued existence and evolution. The mechanism behind this hypothesis rests on the idea that without sufficient observers distributed throughout the universe measuring and collapsing quantum states, the fundamental fabric of reality might begin to lose coherence, with the wave function of the entire cosmos potentially uncollapsing back into a state of pure potential and superposition. This would represent a kind of heat death or cosmic dissolution, not through entropy alone, but through the gradual reduction of conscious observation in the universe as stars burn out, civilizations fade away, and the universe grows cold and empty. The persistence of this hypothesis, despite its seemingly illogical and almost metaphysical nature, speaks to our deep uncertainty about the role of consciousness in physics, and our continued struggle to interpret the mathematical foundations of quantum mechanics itself. We have become oddly comfortable with the notion that reality might be fundamentally dependent on observers, that the universe might require conscious beings to collapse its wave function and maintain its coherent existence, even as our most rigorous experiments and observations seem to suggest that nature operates according to impersonal mathematical laws that care nothing for our awareness or measurement. Imagine the universe reaching a state so profoundly empty that not a single photon travels through the void, not a single particle vibrates with energy, and not a sound, though sound cannot exist in such a place, would ever be heard again, and this is the concept known as cosmic silence, a theoretical endpoint where all matter has decayed into radiation, all stars have burned out into cold cinders scattered across an infinite expanse. And every black hole has evaporated through Hawking radiation into nothingness, leaving behind only the faintest whisper of microwave background radiation cooling toward absolute zero. The real-life foundation for this idea emerges from our understanding of entropy and the second law of thermodynamics, which suggests that systems naturally move toward disorder and dissipation, meaning that given enough time, the universe itself must eventually exhaust its usable energy and fall into a state of complete equilibrium where nothing changes, nothing moves, and nothing can ever happen again. Cosmologists observe that stars are burning through their fuel, that galaxies are moving apart from one another at an accelerating rate due to dark energy, that protons themselves may be unstable on timescales of 10 to the power of 34 years. And from these observations emerges the mathematical certainty that the universe is on a one-way trajectory toward heat death. A state so distant and so profoundly alien to our experience that we can barely conceptualize what it would mean to exist in or observe such a realm. The psychological mechanism that allows us to contemplate cosmic silence without descending into existential terror involves a kind of temporal distancing, where we place this event so far in the future, beyond the lifespan of atoms themselves, beyond the existence of anything we understand as life or consciousness, that it becomes almost abstract and removed from our immediate concerns, allowing us to study it with scientific detachment rather than visceral dread. What persists despite its logical inevitability is our stubborn insistence that meaning, purpose, and continuity matter even in the face of this ultimate ending, as though acknowledging the theoretical reality of cosmic silence somehow diminishes its impact if we simply treat it as a mathematical problem to be solved rather than a fundamental truth about existence itself. Yet this very act of defiance, studying the equations of our own extinction, naming the silence we cannot hear, becomes a form of meaning-making in itself, a human response to the indifferent mathematics of the cosmos that transforms cosmic silence from mere endpoint into a mirror reflecting back everything we choose to value in the present moment. In this light, every scientific discovery, every work of art, every moment of connection becomes not a denial of cosmic silence, but an affirmation of presence within it, a deliberate choice to kindle light in a universe that will eventually know only darkness.